How do we look? The audio's go okay and everything? Okay, let's get going. Okay, last week's readings, we're going to go through both of these today. And there's one more reading that I'll post if you haven't made your 10 or you just like lots of readings. I like this paper. It's different. It's a non-SRAM based FPGA, which has some different trade-offs. Non-volatile, wakes up right away, doesn't need a separate programming chip beside it, and much more radiation tolerant. So if there's time at the end of this lecture, I'll talk a bit about like SRAM upsets and what you can do about them in FPGAs. But one of the things you can do is just don't use SRAM, which is what this chip does. So, what's that? No, that's not good. So that's worse. Okay, administration. No lecture next week. I'm at a conference in China, and you guys had a lecture on Reading Week, so you earned yourself an extra break at the end of the lecture, or at the end of the course. We're going to have a final test. It's in the lecture December 9th. We'll start at 5:10 p.m. It'll be about 60 minutes long. You basically know the format from the previous one. If you found the previous one was fine, this will be fine too. It covers the lectures, the background part of the lab, like there's something in the lab that you should read and understand. That's fair game. And the mandatory readings. So yeah, it's not intended to be super hard. Basically, if you've been keeping up with the course material, you'll be fine. Course evaluation. Oh, actually, I forgot to put this on here. There is one last assignment, which I'm going to release today or tomorrow. It's not as hard as the other three. You basically are doing architecture studies of routing architecture, so you don't have to write any code, except maybe you'll write a script. You're going to be running the VTR CAD tool. So this is one last assignment, but because it's the end of the course, it's not as time-consuming as the other ones. Course evaluations are open on Quarkus. They're available till December 3rd. Actually, 23% of people have filled it out before I even nagged you, so that's a good, actually, for that. It's hard to get people to fill out course evals sometimes. Feedback's really useful. I read all of these very carefully, and I've gotten lots of good ideas in the past of like do's and don'ts. So I encourage you to fill it out. It is appreciated. And you know, if you have any feedback, it's very helpful. So you know, are there topics that I should definitely keep because this was like your favorite part of the course, or the things where you go, this wasn't very useful, so I should either revise it or remove it. The course material is basically full, so it's kind of a zero-sum game. So it's actually useful to be told things that like if this part is not resonating or it wasn't that good, then I can take it out and do something else. I did a test this year versus a term paper, or a couple of tests. You haven't written a term paper, but you could tell me I really, really wanted a term paper. Next year you should do that, or maybe you were like, I hate term papers. Thank you for doing a test. If you don't care, don't say anything. Anything else that you want to comment on. So it is very helpful. Assignment 2 contest. Okay, so this class is like a bunch of like extreme keeners, okay? So you guys hit like a level of optimization that I have actually not seen before, so I got to think carefully about exactly how to revise. How to make sure I make all the rules super 100% concrete. So I decided there's a 3-way tie for first, because it was just too hard to tell apart. So Mark, Gavin, and James, I will send you Amazon gift cards through some kind of electronic form, so you don't have a physical thing you lose. So both Mark and Gavin actually went all the way to optimizing for the FIR filters, but basically made one piece of hardware that could handle all the convolution coefficient filters that you were given across the whole test bench. So one design could handle them all, and basically wrote logic to decide which filter you're using and do lookups to make the soft logic more efficient and actually faster. And I put that in italics because you know basically this is what I need to make sure I make the rules super clear. But that's the highest performance implementation. For one that doesn't use the trick of basically adapting to the limited set of filters I gave you, basically James got the highest performance on that. He used soft logic. He exploited the fact that the filters are two-way symmetric, and actually found that soft logic could clock faster than the DSP limit, so got it to 640 megahertz. Gavin and Mark also actually optimized that case and did very well on it as well. So I decided, okay, fine, I'm not going to, all three of you are like tied for number 1. There's only a small gap to Adam, who got almost the same peak throughput as James, and did actually get the same peak throughput on that case as Mark. So maybe this is like a 1.5. You could come, this is bordering on like a 4-way tie. Used soft logic and DSP, two-way symmetry, hit 549 megahertz. Zenrong is only slightly below that. And you also use two-way symmetry of the filter to reduce the number of DSPs, and then used an interesting trick of basically realizing that with an 18-bit multiplier, you can pack two 8x4-bit multiplies into that. So you put some in the low order inputs, some in the high order inputs, and you take out you pull out from your 32-bit output two multiplies. However, in order to do this, Zenrong had to basically do it unsigned to avoid contamination between the bits. Like when you try to pack two multiplies into a bigger multiply like this, you have to worry about if your results start to overlap in the output. You can't tell what's what anymore. But by using unsigned multipliers and doing the sign correction in soft logic, was able to pack basically double the amount of multiplies into the DSP blocks. And in prior years, all these solutions would have won. Okay, so it's like this is like the 2025 like annex, right? So Islam, Ahmed, Yulang, Mohammed, Raphael, and Angus. Well, 5 of you maxed out the DSP block performance, used one-way symmetry, and maxed out the clock frequency. It was actually interesting, and some people figured out they could clock faster if they just used pure soft logic. And Islam took a slightly different approach, mixing, using the DSP block and two-way symmetry, but didn't get quite as high a clock frequency. So, okay, so anyway, so well done. There will be some Amazon gift cards going out. So I'm going to give a round of applause to the class, because this was very... yeah, they were great solutions, frankly, actually. So I went through and read a bunch of the optimization of this, and I was like, well, this is quite impressive. So, okay, so on to the course concept map. So we're on the last lecture talking about interposers, NOx, and a few variants of things that could be called CG arrays. So CGR is a pretty broad bucket. So we'll talk about a few different things that you can call CG arrays, which stands for coarse-grained reconfigurable array. So something that's related to FPGAs, but not exactly an FPGA. Okay, so we were talking about interposers. And I showed you this figure just before we broke last week. This Xilinx Vertex 7, and Xilinx has used this same kind of structure in all of their FPGAs since then. So remember, they've got, in this case, they've got 4 28 nanometer FPGA dice. They've flipped them upside down, and they have these micro bumps, so smaller bumps that connect to another piece of silicon, which is made in a less aggressive process. So in this case, 65 nanometers. And this interposer just has wires, connects together all of these FPGAs to make something that behaves a lot like one big FPGA. That's what you'd ideally want. And then you also have bumps coming out of the other side of this silicon interposer, which connect to your package. And in your package, after you go through all its signal traces, you have even bigger solder balls that will connect to your circuit board, okay? So hopefully you remember that. This is a more detailed picture of the physical implementation of this interposer, and the technology that Xilinx is using is called CoWoS, so it's a TSMC technology. I think Xilinx was the first company to actually use this. It's the first one that I ever saw use it. It stands for like chip on wafer on either substrate or silicon. I forget what the S is for. Do you have a question?
So ignoring the cost, if you have the interposer die,
yeah,
like on a cutting edge node, do you get any scaling benefits from that?
You're saying like the 65? Like why do 60? Yeah, probably not. The reason is you're going to be limited by these micro solder bumps. So these micro bumps, I think I have it on this slide, how big they are. So these micro bumps, their pitch is 40 microns. Okay, so, and you can see 40 microns, this is 1,000 microns, okay? So that's what you've got connecting you to a circuit board. So, you know, a pitch of that, you take that squared, 25 squared times. So 625 times as many microbumps I can fit on an area of silicon compared to these solder balls. The bumps, the regular bumps that would connect me to the package, you know, are not quite as big as these solder balls, but they're 200 microns. So that's let's see, 50 times, still like 2,500 times less density. Is it 50 times? Let me think about that. Let's see, 0.2, no, it's not 50 times, 25 times less density. Okay, so anyway, so I guess that shows why do I want these micro bumps. But 40 microns, much better than these regular bumps to the package and way better than the connectivity to the package. But 40 microns is still pretty big compared to a metal trace. Okay, so that was a 65 nanometer interposer. So I can make wires that are some multiple of 65 nanometers. And this is 40 microns, which is 40,000 nanometers. So I'm not going to get any benefit from the ability to make finer metal. I'm going to make pretty wide metal traces and pretty big landing pads. Does that make sense? I'm also, you're going to see that these wires here that go through the interposer, they extend a reasonable distance because I have to get enough solder bumps and I can't put them all right on the edge of this FPGA chip. So some of these wires are reasonably long, like maybe a few millimeters long. That means I want them pretty high in the metal stack, and I want them pretty wide, and I want them pretty thick. They can't be very resistive. That means that even in 65 nanometers, I'm not going to use the thinnest wires I can make. I'm going to be using relatively thick metal wires. Still way better than what I can make in a package, but yeah, if you turn this into like 28 or 20 or something, I'm just going to make the same wires anyway. So I'll just pay you more for the silicon. Yeah?
Just to confirm, there's no configurability in that interposer. They're just like point-to-point connections.
Yeah, this is passive. Okay, to save costs and to make the manufacturing easy, this is a passive interposer, meaning you're only fabricating the metal stack. There are no transistors on this die. Okay? Yeah?
I guess on that note, is there any, economic reason, or I guess, is there any reason you would want this not to be passive? And would it, I guess, make sense
I mean, there are reasons you might, so once you go beyond passive, it's no longer called an interposer, right? I mean, maybe there are things called active interposers, but generally once it's no longer passive, you're talking about like essentially 3D integration techniques, like die stacking. I'm not going to talk about that because I'm running out of time, but if you're interested, I've got a reference to a paper on, VTR was made 3D aware and was used to do some studies of how could you do this. Once you make it active, you usually call it 3D integration, and you're able to just stack different dice that can do everything. Interposers are sometimes called 2.5D integration, because you are stacking things, but you're kind of limited in what you can stack. These interposers are only providing connectivity. Does that make sense? Okay, so this hopefully gives you an idea of the scale, though. So up here, you'd have really, really tiny wires on the FPGA. Then you got these micro bumps. The interposer. You need to have some connectivity. I talked about this in last week. I need to get power to this FPGA, so I need some through silicon vias. I also need to get IOs from the FPGA, out to the circuit board. So again, I need through silicon vias. So these are like vias that literally go all the way through this interposer. So they're much taller and much bigger, so they don't become kind of impossible to fabricate than a regular via. But that's fine. You can build them. Okay. Okay, so why would we do this? So I kind of gave you the two reasons. One is to make a bigger FPGA, because I can sell it to companies. Companies that are making, for example, like really high-end networking, like say Cisco, they would tend to buy, they were a market for high-priced FPGAs, like our big FPGAs, because they want to make the next generation system. And companies that are doing ASIC prototyping. So like Synopsys and Cadence, when they're making these ASIC prototype systems, they need to sell you a huge number of FPGAs to fit your ASIC, or a large number, tens, maybe even more than tens, maybe hundreds. And it's a pain. You got to partition your design into all these FPGAs, and you run out of IOs and so on. So if they can give you a bigger FPGA, they'll pay for it. So that's one reason. And the other reason I said was just you're going to make the same size FPGA, but you want better yield. So let's talk about yield. So a monolithic FPGA is just like a traditional FPGA, right? One piece of silicon. So, and what I've drawn here are basically a bunch of dice. Okay, so when you make a semiconductor wafer, you repeatedly pattern the same thing over and over again. That's called your reticle. And then you're going to saw these into chips. And the manufacturing process is imperfect. There might be a tiny piece of dust. There might be a little flaw in the photoresist, whatever. All these dots are defects. Any one of these dice that is hit by a dot is not going to work unless I built redundancy in. Okay, so I talked a couple weeks ago about how Altera has redundancy. So Altera FPGAs could actually recover from some of these, but for most FPGAs, they won't. Any dot lands on you, you're dead. So you can do a little bit of math, and it's kind of intuitive. Your probability of working is basically exponentially related in a negative sense to your area times the defect density. So in order to work, you basically got to dodge all defects. So the bigger you are as a chip, the lower your yield is, the higher the defect density is. So what's the expected number of defects per square centimeter? The worse the yield is. So what are reasonable numbers for this? So let's say I'm making a big FPGA. So it's going to be a high-end FPGA that I'm going to try to sell to Cadence, Cisco, gullible researchers, whatever, right? So that's pretty big. It's not quite at the reticle limit, which is a little over 8 squared centimeters, but it's big. And let's say it's relatively early in the process lifetime. So it's cutting edge, just came out. My defect density is one per squared centimeter, which is reasonably high. Defect data is like super secret. Like if you want to get like semiconductor foundries to like chase you down, try to get their defect density. These are realistic numbers for like early in the process though. Okay, so if I put this into that model, the yield is like basically 1/4% of my chips are expected to work, which is pretty bad. Okay, so if I work out, well, how many of these chips can I fit in a 12-inch wafer? It's 730 divided by 6, okay? And then I multiply by what fraction of them work, and I actually get 0.3 chips per wafer. So I actually am now like wafers per chip. I actually have to fabricate 3 wafers to get, on average, 1 working chip. So this is pretty bad. I'm going to have to sell this chip for a huge amount of money. I probably really can't even sell it. If I actually get a significant order for this, at this kind of yield, I'm pretty worried I just can't even source it, right? I'm going to have to run too many wafers. All of these defect densities, they're not completely stationary over time. So if I have like the foundry has a bad 2 months, I might get no working chips. So probably this will be at least really expensive, and there's a risk that it's just not manufacturable. Yeah.
Just to have a point of comparison, what's the yield percentage of like a regular kind of like mid-sized chip?
So I have that on the next slide. It's like the best question ever, right? So, okay, well, I don't have it on the next slide. I have it in 2 slides, okay? But basically, so the analysis I'm doing right now is skewed towards favorable for interposers. Big chip, early in the process cycle, so the defect density is pretty high. So let's say instead of making this one big chip, right, 6 square centimeters, I make a smaller chip, 1.5 square centimeters. And I'm going to combine 4 of these on an interposer, just like Xilinx did, to make my big, equivalent logic capacity chip. So what's my yield? Well, if I plug in my same defect density, but my area is going down by a factor of 4, my yield goes from 1/4% to 13.5. Which is still, it's not fantastic. I'm only getting about 1 in 8 chips working, but it's now manufacturable. That's like a reasonable yield. My die per wafer, it goes from like 0.3 to 66 because I also get more dice per wafer, right? That each chip is much smaller. I have to take 4 of those working chips and put them together on an interposer to make a system. So I got to divide by 4, but I can still make 16.5 systems out of 1 wafer on average, which is a 55x increase. So it's a huge gain. And again, this is the analysis that you'd be doing if you were Xilinx. If you could repair a lot of your logic, so Altera can repair most of their chip, although they can't repair all of it, like the IOs are generally not repairable, for example. So their analysis would be different. But it looks pretty good, right? If I want to make a really big FPGA and I want to ship it, like really big FPGAs are also nice to put on advanced process nodes, because again, you're trying to make the highest capacity you can. So it's like a good combination. And for those, there is actually a really big yield improvement. So that's what Xilinx was going for. Now you have to ask, well, I have to put these things in a wafer, right? 4 of them. Or on an interposer. So what's the manufacturing yield of actually bonding these to the interposer? And it's very high, okay? So it's not 100%, I've neglected that, but it is quite good. So this is pretty close to what you'd get. Okay, but you had a great question. What happens for a smaller chip? So let's say that I'm doing a mid-range FPGA. So this isn't like a really low-cost one. This is 2 centimeters squared, usually about, if you look in, an FPGA company makes a new family of FPGAs. They usually make about 6 or 7 densities. This would be the one that's kind of in the middle or maybe a little bit below the middle. And that's the one they expect to sell lots of, right? The one that's really big, they expect to sell much less of, but they're going to charge a lot for it. This is kind of the workhorse. And let's also change the defect density. So the defect density does go down over time. And foundries work incredibly hard to get that defect density down. So a realistic number for a process that's a bit more, that's significantly more mature and has had some time for them to work out what are the flaws and fix them, you'd have a defect density that's like 0.1, so 1/10 of what we had before. If I basically calculate the yield for that, I get 82% of the dice are going to work. So my die per wafer for this chip is 299. Now I could use an interposer for this. I would make 4 chips that are each 0.5 centimeters squared. My yield is even better. It's 95%. And I would actually get a few more systems. So instead of 299 systems per wafer, I could get 347. But this is not super compelling because there is a cost to making the interposer. There is a cost to assembling it. So it's probably not worth doing for this size. So it really is for the big chips. Does that make sense? Okay. So let's look at what happens at these die crossing boundaries. So in the Vertex 7 series, where Xilinx pioneered this, they have the total number of vertical wires they have in their big FPGAs is they have 280 routing channels, and the width of each of those routing channels is 210 wires. So you can just multiply those together, and you can say, what's the total amount of wiring, crossing some cut line, right in the middle of one of the chiplets. They can't get all those wires across the interposer, and they can't get them all across the interposer because they can't fabricate enough microbumps, right? The microbumps are still a lot bigger than regular wire traces. They were able to get 48 of the wires in every routing channeled across the interposer. So they got about 23% of the vertical routing to go across the interposer. And it had a higher delay. It has a higher delay because they have to go through a solder bump twice, right? Once going down to the interposer, once coming up. So that's going to add some delay. But the other effect is I can't put all the solder bumps right on the edge of the chiplet, right? They won't fit. I have to start pulling them back to get enough space to put my solder bumps. So some of the solder bumps are actually like, 2 or 3 millimeters away from the edge. And then that means I need to have a relatively long wire in that interposer before I come up on the other side. So I've got to add all that in. And the delay that Xilinx had for these wires, or has in Vertex 7, is about a nanosecond, which is about 5 times the delay of their kind of workhorse regular length routing wire in their routing channels. So it's not catastrophic, but the wires are noticeably slower. And wherever I hit one of these chiplet boundaries, I can only get 23% of my wires across there. So is this going to work well? Maybe this is going to just turn into a huge routability problem and nothing's going to route. Yeah? I guess in a way, you're right. So they have created a cut line here for physical reasons. So the nice thing about this is I think the way Xilinx packaged this is actually very clever. They didn't explain this to their users or package it as like 4 FPGAs that you design for, and then you have some I/O between them that you plan, etc. I think that would have been much harder for people to use. So what they did is they just said it's one big FPGA, okay, with this interesting technology under the hood. So you just do your design normally. There's no need to partition your design. So if you actually make a design and you say, I'm going to use 3 or 4 FPGAs, then it's your problem to cut it up into pieces that fit in 3 or 4 FPGAs and don't exceed the I/O count. So Xilinx did not make people do that. They said, we'll hide that, we'll take care of it. Another thing that's done in ASIC prototyping is because the number of I/Os between these FPGAs that are working together to emulate an ASIC is so limited, so much less than what you'd want, is they will time domain multiplex the IOs. So slow the system down, but send multiple signals over time. So Xilinx didn't do that. And the reason is they don't want to just have this for ASIC emulation, right? It's hard to integrate time domain multiplexed wires into somebody's design. So they don't force that. So it looks like a single chip to the user. Their placement engine, they've never said exactly what they did, but it's presumably been modified to minimize the signal crossings across these chip boundaries. So the question is, will that work well with the connectivity available? So Xilinx has never released their results. Clearly they thought yes, right? Because if they thought no, this is probably an act of insanity, right? So you can assume they have some internal data that this is going to be okay. Yeah.
Just curious, like, are the 4 dies that are being glued together, are they the same?
Yeah, for Xilinx they're the same. They make 4 identical dice. So we did some experiments with VPR, so we augmented it, where we could basically remove a variable fraction of the wires and basically play with, and we changed the cost functions, et cetera. Also could use partitioning to help seed the initial placement and so on. And if you're interested, you can go read this paper. But basically, what we found is that it was actually okay to cut about 80% of the wires. So with that CAD tool, so a modified version of VPR, where we've worked a reasonable amount to make it optimized for this, what this is showing is how wide do the routing channels have to be versus what percentage of the wires get cut at the interposer boundary. And we could basically cut about 60% of them, and the CAD tool is basically happy, right? Like it could find, is changing the placement, so it is moving things so to try to minimize how many wires cross that, but it's not really making routability worse. Like we don't have to widen the rest of the routing channels. After that, you start to notice some degradation, and beyond about 80% is basically, it can't really do it anymore. It's basically become limited by that interposer crossing and is effectively saying, you gotta give me wider channels everywhere or it's not gonna work. So Xilinx, for Vertex 7, they're right around here. Okay, so it looks reasonable. They're in the spot where this is not causing big problems. And with CAD tools, it's actually easier to prove a positive than a negative. Okay, so it says that there are algorithms that are published that can achieve this level of quality. It's also possible there are better algorithms, right? So Xilinx might do even better than this because they have lots of money to spend. But it looks pretty promising. Yeah?
Just curious, was this experiment done with benchmarks that utilize more than one FPG, that like really large benchmarks?
That's a good question. I mean, we always size the devices so that you had to cross 3 or 4. Like you couldn't put it all on one side, right? So now one of the things that the study was done a while ago, you'd ideally like bigger benchmarks. So certainly a critique that you could make of this work is the benchmarks are not as big as what you'd put in these really big interposer designs. But essentially the system capacity is shrunk so that every design was like, you've got just enough space, you're gonna have to cross these boundaries. But that's a good question. Yeah?
I guess, because like at some point you increase the minimum, the minimum channel width beyond 60%. Like you're saying around 80% is okay. When does it become?
Well, I mean, as it's starting to go hockey stick here, this is really bad. One other way to interpret this is we can basically say, let's take some wires out of the interposer crossing, like only 10% cross. And it's like, oh, that works fine as long as I double all the channels, which actually puts all the wires back again. Do you know what I mean? So it's basically the CAD tools are really struggling here. Maybe it didn't quite double the channel width. I guess it hasn't doubled it, but out here it's getting close. So it's basically just going, I really can't, I'm getting super limited by these solutions. Here, it was fine. Here, there's maybe a little bit of negative feedback, and out here, it's kind of crazy. There are various papers from people using these Xilinx chips that have occurred over the last 5-6 years that basically say, yeah, they're definitely usable, but you can get into trouble at these interposer boundaries. Okay, like you can get into some routability trouble, some timing trouble, all of which kind of lines up with that we're kind of in this domain where it's kind of mostly okay, but it's not completely invisible. And it depends a bit on your design. So one of the other things that a good question is what will happen in the future? Okay, so micro bumps haven't scaled as well as just regular wires, which means that I can get 23% of my wires across in the 28 nanometer generation. Maybe in future generations it'll be less. So that would put increasing pressure on this. It's hard to say. It's going to depend on how those scale. Micro bumps, yeah, are scaling slower than interconnect, but there's an even newer technology called hybrid bond, which basically gets rid of bumps entirely and does direct copper to copper attachment, which gives an even higher density. So that would make it, so who knows, right? There's some pressure that if you stick with micro bumps, this could become a somewhat harder problem generation by generation. Some of the things that we found in this paper are that, okay, these interposer wires are clearly very valuable, right? They've got a pretty big micro bump on each side, a pretty big driver, and you can only make so many of them. So it was useful in the architecture to make the muxes that can drive these wires bigger and to make the wires bidirectional. So this would be another one of those expensive wires where direct drive is maybe not the best choice. So to get this result, we did also change the routing architecture some to try to make these wires as usable as possible. And the area of cost of that was small, so it was fine. Okay, so Altera also uses interposers, but they use them in a different way. So this is a Stratix 10 device, and they use these things that they call advanced interconnect bridges, which is, and sometimes they call it EMIF, so they call it both things. Basically, these are small interposers. So instead of having one big interposer that is underneath all 4 of those Xilinx chips, Altera makes, in this case, 6 small interposers. And they don't make identical chiplets. They make one big chip that's essentially a monolithic FPGA. But they put the high-speed IOs, the serial transceivers, on separate chiplets. And the reason for that is that they can use a different process technology for this. And sometimes there's a little bit of analog circuitry in these serial transceivers, so they may have different preferences in terms of process technology. So it takes a very complicated block and puts it on a separate chiplet. And it does allow them to do some mix and match. They could actually change their I/O technology now much easier because they don't have to retape out an entire chip. Yeah?
And another benefit to this, the CAD tools are significantly easier because you don't need to worry about those interposer line cuts when you replace them right.
Yeah, this is basically invisible to the CAD tool, except from the point of view of like the timing, right? So this is going to be, maybe you put some registers here, you put some registers there, and the CAD tool is told, here's the timing to this register, and they better make sure that you can get across in one clock cycle, because if you can't, there's nothing the CAD tool can do. So yeah, from the CAD tool's point of view, it's like the timing's a bit different, but there's none of this complicated optimization. So here's what these two things look like, kind of with a slice through. So I already showed you this. This is what Xilinx is using. This is the next generation, ultra-scale, but it's the same technology again, right? So the piece of silicon, and then on top of that, you put the FPGA dice. And Intel basically would hollow out a little piece in the package substrate, and they'd put a small piece of silicon in there. So an interposer calls an embedded interconnect bridge. And that interposer was just big enough to connect the I/O die to the FPGA die. So the trade-offs on this, so CoWoS, which is a TSMC technology, it was originally limited to the reticle limit, okay? The reason it was limited to the reticle limit is it's a piece of silicon. So they have to actually image that silicon using the same semiconductor manufacturing equipment. So it meant while your yield was much better and you could go all the way to the reticle limit, you couldn't go beyond it because you couldn't make an interposer big enough. However, this limitation has been relaxed in the latest versions of CoWoS. TSMC can now do 3.3 times the reticle limit. They don't say much about how they can do it, but I looked through some of their literature, and what it looks like they're doing is they're overlapping. I mean, they basically say this, but without a lot of detail. They're overlapping the exposures. Okay, so the reticle is how big an image you can print, which is basically the size of chip you can make, and then you move on to print the next chip beside it. So they're making those overlap. So if you use a somewhat relaxed metal pitch, you're not going to be able to align that as well as you can your usual within a reticle imaging. You'll be able to have interposer wires, well, an interposer that's bigger and still has wiring everywhere. And that's not an unreasonable thing to do with an interposer because you're connecting to it with these micro solder bumps, so you can't make use of incredibly thin wires anyway. Does that make sense? And that now allows them to make bigger systems. Yeah?
It's like basically just multi-patterning.
Multi-patterning is different. Multi-patterning is within one reticle. Multi-patterning means, okay, so how many people know what multi-patterning means? Do you know that term? Okay, so a few people. Does anyone want me to explain it, or you're like, please stop? Okay, so multi-patterning is an approach where you basically expose the same thing multiple times to draw smaller features. So it's kind of going the other way. This is like a shift and then overlap the two exposures so that you could have some wires that connect between them. And because that shift is they're going to not be able to align those two separate images as well as they can align things within one image. They're going to have to use a relaxed metal pitch. That would be a problem, on the really fine wiring deep inside an FPGA, but it's presumably much less of a problem on the relatively coarse wiring that you needed on an interposer. So EMIB, the Altera Intel technology, can do arbitrary system sizes in theory because it uses multiple interposers. You just have to keep making little gaps in your package and just keep making things bigger and bigger. So that's an advantage of it, although CoWoS may have weakened that advantage with this new technique. With CoWoS, when you look at the connection from the FPGA to the package, it has to use a through silicon via, right? Like the interposer's in my way. My FPGA wants power. My FPGA wants to send a high-speed serial output or some high-speed I/O. It has to go through this through silicon via. And that has some resistance, which is important for power. You would like that to be 0. And it has some inductance, which is important for high-speed serial or high-speed source synchronous interfaces, because that's going to affect your signal integrity. It's tolerable, right? That's why you can build this, but it's undesirable. With EMIB, you don't have that. The FPGA die can attach directly to the package substrate, so can the I/O dice. So you kind of get rid of a layer that you'd rather not have on your power or your signal path. In the future, we could stack multiple active device, right? So this is a question about, well, what if you didn't make your interposer passive? I don't have time to talk about that, but if you're interested, you can go read this paper by Andrew Boutros and a bunch of other U of T people that talked about exactly that, right? So could we stack 2 FPGAs on top of each other? Could we stack an FPGA and something else? And what would the CAD tools have to do? And the short answer is it actually looks like it works pretty well. So it depends on how good your integration technology is. But if you have pretty good solder bumps, like micro bumps, you can actually stack an FPGA on top of another one or stack other interesting things on it, and it works quite well. If you have what's called hybrid bonds, which is even smaller than micro bumps, then you can do really well. You can make something that where the 3D FPGA really looks like an extension of 2D. Yeah?
I guess for the CoWoS, did it need to be like one large interface with all the guys you stacked on it? Could it have been multiple interfaces and pieces or something similar to what I guess,
Yeah, I mean, that's what EMIB does. So I guess the answer is both are possible, because Intel manufactures, it's not just Altera in this case, this is like Intel as a manufacturing company now. They make EMIB devices for all sorts of things, but FPGA is one of the early leaders. TSMC has pushed CoWoS. So technologically, both are feasible. I don't know if TSMC will one day also allow, mix and match of both. It's possible. They have now 3 different variations of CoWoS. So I dug into their literature some more to see what's going on before this lecture, and that's where I found they can do 3.3 times the reticle limit. They have a lot of options. So, although I didn't see that one. So.
So I guess for EMIB, could the die on the left communicate with the die on the right, or does it?
It can only communicate with the die on the right through this FPGA. Okay, because this is a signal trace that's connecting this micro solder bump to this micro solder bump. So you can have a whole bunch of those. That in the case of Altera, they're using that to get to their high-speed I/O. There's no direct path from this guy to this guy. So, and in fact, with EMIB, you couldn't do it. Like, it's just not possible because this interposer is this big. There's no possible way you could get to here except by going through here.
I guess would it be the same thing with cross from the left side to the right side?
I mean, you could physically make a wire that went all that way. However, that wire is probably so long that even if you make it as fat as you can and as thick as you can, it's probably still too resistive, right? So the wiring on the interposer, yeah, you are making quite a bit wider and thicker so that it's not so resistive, but it's still, if you say I'm going to go 20 or 30 millimeters, it's probably still going to be bad. And you don't have the ability to put a buffer in. Like your standard technique is put a buffer in. I can't. I've got no transistors. Only way I can put a buffer in is go back up. Actually, in Xilinx's most recent devices, they do another interesting thing with this interposer. So, okay, so I showed you in Vertex 7, they basically have solder bumps near the edge, and that gets them enough connectivity between the dice. But this interposer is actually underneath the middle of the FPGA too. And for many generations, they didn't do anything with that. But in Versal, what they actually do is they have some solder bumps to go to the interposer, get to those fat wires, and use it to route a long distance and come back up into the same FPGA die. Because basically, I told you that like for long wires, they have to be thick, and you run out of metal that can do that. So Xilinx basically decided, well, wherever I've got interposer metal that's not being used, that's like thicker and wider than anything I can build on my 28 nanometer or 7 nanometer FPGA chip. So I'm going to use that as another level of interconnect option. So yeah, now they will actually use it even to go pop off of one spot on the same FPGA and get it on somewhere else. Let's see. I think that's all I have on interposers. Any other questions on that? Yeah.
What are the power considerations of interposers? Like, there must be like a cost to crossing these interposer lines.
It doesn't cost you any power, or not significant power, because I mean, this wire has more capacitance than a regular wire, so there's some impact.
Gotcha.
Because you don't have that many of them, it's probably not too bad, right? So there's a bit of power impact. Your bigger power impact is the fact that I have to bring my power through this through silicon via,
Right.
which adds resistance and some inductance to my power network, which is undesirable, right? So I probably have to, you can deal with that though by bringing power in more vias. Right? The more times you bring power in, less parallel resistance, less parallel inductance. You care about resistance, but obviously, this is obvious, but so these things draw a fair amount of current. If I'm drawing 50 amps, and even like a 10 milliohm, so 0.01 ohm times 50 amps is, see if I can actually do this. It's like way harder to do math than you guys can ever believe once you do this. So 50 amps times like a 100th of an ohm is going to be, that's like 0.5 volts, I think. Is that right? Okay, so that's way too high. Okay, so it's going to have to be more like a 1,000th of an ohm. So you can, because you don't want to drop much. Like the whole power supply is maybe 800 millivolts. So I don't want to drop any more than maybe 10 or 20 millivolts of resistive drop. So if I'm drawing 50 amps, let's say I'm drawing 100 amps, okay, and I only want to drop 10 millivolts, I can afford like, 0.1 milliohms, right, in this power delivery network. So even though these through silicon vias are pretty thick and they don't have that much resistance, I have to be pretty careful. So I may have to add more through silicon vias. Inductance matters because when you actually change what the chip is doing, suddenly you get a power drop. And you want to minimize that too. So clearly it's manageable, right? I haven't heard stories of Xilinx chips failing in the field, but it's something they would have had to be careful about. It's something in this paper that we looked at for 3D chips. How do we get the power to them? Because if you can't make the power supply robust enough, it's bad.
Sorry.
Yeah.
Is that the primary reason why, like, I think Intel has a thing on, like, backside power delivery?
Yeah, backside power delivery is to reduce the IR drop to your transistors. Okay, because the more your IR drop to your transistors is, you essentially have to take it out of the speed of the chip, right? When you make the timing models, for example, for an FPGA that go into Quartus or Vivado, et cetera, you have to assume a voltage when you're doing all the simulations, and that voltage is reduced by whatever you think like a kind of the worst case IR drop would be. So backside power delivery is, actually, this may not be comprehensible to people. Usually the power to like a chip comes through its top level metal, okay? So let's forget about interposers. You just flip a chip upside down, and you bring power in through the solder bumps, and it goes through very thick metal that's at the top of the metal stack because you want the thickest metal you can get, so it's got low resistance. And then it drops down through a whole bunch of vias to get to the transistors. And it still has some resistance, and you have to take that resistance into account when you decide what voltage really hits the transistors. And you'll often drop 10 or 20 or 30 millivolts, which you don't like, right? That 10 or 20 or 30 millivolts is like 3 to 5% of your speed is gone. So you'd really like that to be lower. Backside power delivery is basically Intel is fabricating wires on the other side of the silicon. So they've got the regular metal stack above the transistors, and then behind the transistors, they've actually built more metal. They've thinned the die. They've put more metal on the back, and they run basically vias up to the transistors. And the idea is they can make thicker, hopefully I'm not giving you any inaccurate information because I haven't gone and read all the details in their backside power delivery, but the idea would be you don't have to go through all these vias, all of which have resistance. You can instead come up from underneath the transistors with a shorter signal path and thicker metal. And you also get out of the way of other things that want thick metal. Like I told you that for clocks, you'd like to put them high up in the metal stack. For your long distance routing, you'd like it high up in the metal stack. There's a lot of competition to go to the top of the metal stack. So getting power and ground out of there is helpful. And it gets rid of all these via stacks that can add resistance and also get in the way of like signals that are just trying to route in the lower levels. Does that make sense? Any other questions on interposers? Okay. Okay, let's talk about NOx. So we're on to the second topic for today's wrap up of all possible topics. So I'm going to go through, there's a bunch of work that was done by Mohammed Abdel Fattah here at U of T and some other students, but he was the leader of a lot of this. This one paper kind of gives an overview of a bunch of it, but some of the things I'll talk about come from other papers. So maybe I'll give some context on it. So I'm mostly going through kind of the academic work that looked at, should we put embedded NOx, like hard NOx in FPGAs? How should we do that? And then at the end, I'll talk about, basically industry has adopted those ideas, and I'll talk about a couple of cases of examples of how they did that. And did they do it the same way as was proposed here or something different? Okay, so most of this is going to be about like academic studies of what you should do, but there'll be some industrial use cases at the end. Okay, so here's the challenge we're trying to solve. So we've got big systems and all these high bandwidth communication between modules, but also especially to our I/O interfaces. So things like memory controllers to DDR, PCI Express to whatever, the host CPU, Ethernet to out to our network. Those are producing lots and lots of data bandwidth. And we can clock the FPGAs a bit faster from one generation to another, but the main way we're dealing with ever higher bandwidths is actually making the buses wider and wider. And we can do that because the FPGAs are getting bigger in capacity, but it's expensive. Okay, so we've got lots of communication on the chip. So the traditional way this is handled is you design what's called a soft bus. So you just program it into the FPGA, right? And the FPGA can make a bus with arbitration and muxing and so on. So we figure out that module 3 needs to talk to module 1, module 2 needs to talk to module 4, etc. And some of them need both module 1 and 2 need to talk to the memory controllers. So we build a bunch of buses and arbiters, and we can make this work. But what we're doing is we're building wide links. So to get enough bandwidth to things like memory controllers, we actually need to make buses that are hundreds of bits wide. So they're, and FPGA interconnect is 1 bit wide. So we have to take 100, 200, 500 parallel routing tracks and use them to get to that memory controller. We aren't always just directly connecting one thing. So memory controllers would be a common case. Things like DDR interfaces tend to be lots of part of your design may want to use them. There may be a bunch of different modules that all want to store some large structures in DDR. And I can usually only have so many banks of DDR. So you can't give each of them their own bank usually. So they'll share a bank of DDR. And the way they're going to do that is basically, these are not just wires now, they're muxes, right? We have to decide who's sending data to the memory controller. When data comes back, who are we sending it out to? We have to arbitrate to say, can't have more than one thing trying to send data to the memory at the same time. So that's muxes and arbitration. And that's logic. So now we're not just using up the programmable routing, we're also using up a bunch of logic. This usually you want to be quite fast. Even with buses that are hundreds of bits wide, to match the bandwidth of these memory controllers, I need to clock this at a pretty high frequency, so several hundred megahertz. I'd like it to be as fast as possible, because if I clock it slower, I have to widen it even more. And it often is going all over the place, right? Lots of things want to talk to this memory channel. So I probably have to pipeline it a lot. And that adds a certain amount of difficulty to my design. I may have to manually change the pipeline depth repeatedly, and it's also going to chew up more area because there's a bunch of registers. And all these buses are unique to the application. So I make my application, I start building these buses, I just have to put in the effort to make it work. Okay, so they're overall costly and a pain in your design process. Okay, so one of the things we learned in this course is if it's common, and these wide buses and these links going to memory controllers and PCIe are very common in designs, and it's expensive, then maybe it's worth hardening. Okay, so maybe we can make a hard bus. Okay, so we do have this system level interconnect in most designs. So what I'm calling system level interconnect is like long distance interconnect between big modules moving a lot of data. Often one of those modules will be like an I/O controller, but not always. Okay, so that is in most designs. Is it expensive? I haven't shown you this, but it does add up to a lot of area and a lot of power. Because these buses are so wide, we need to put pipeline registers and arbitration on them. Okay, so it meets our requirements to harden it. Okay, so I've got this great idea now. I'm going to harden that bus. So I'm not going to do it. To see that it turned black. It's not made out of the programmable routing anymore. These are dedicated wires. I put them in my FPGA. I put down a bunch of muxes that I pre-built, arbitration. This is my special bus block, another special bus block, another special bus block. All these wires are done. And now I got this design is way more efficient because I got rid of all sorts of soft logic and programmable routing and replaced it by much more efficient hard logic and prefabricated wires. So is it good? What do you think? Okay, so I see Amir is shaking his head. Why? Why don't you like it?
This only works for this particular design.
Yeah, so it passes some of my requirements, but it's not usable by many designs. Like basically, I built this thing. Okay, it's great for this one design. Now I change the design. Okay, so I change the design so I take out all my modules. I still have all this hardened stuff that I put in. So I just put buses all over the place, wires, arbiters, etc. I put in my new design. And my new design has completely different modules that want to go in different places, connect to different things. And it's like completely unclear how I can use these like highways to nowhere, right? So this, so this is not good. This sounds crazy, but there was actually one of the Altera chips. Effectively, there was an architecture proposal that some senior people really liked, and that was effectively this, like basically building like a hard bus down the middle of the chip for DDR, because DDR traffic was such a pain to distribute, but it was basically just hardened wires and muxes, and it was going to be up to like the CAD team to figure out how the heck can you use this. So my nickname for that architecture was TTC, right? So we're just building like subway lines to nowhere. So anyway, we were able to kill it, but it was seriously entertained. So, and the reason it was seriously entertained is because we were chewing up so much logic, right, in building these soft buxes. So, but this is a case where hardening the direct thing that's a problem doesn't really work. Because once you harden it, it's just too inflexible. So we can't take this direct approach. Okay, so what we need to do if we want to harden something here is to have a more general system level interconnect. We need to move data between arbitrary endpoints. So the big problem here was we couldn't move data between arbitrary endpoints. We're just building buses, but the buses may go to some place that nobody wants to be. So we have to go between arbitrary endpoints. We want it to be high bandwidth. So FPGAs are quite good at all the low bandwidth communication. We've got a good solution for that. We've got an acceptable solution for high bandwidth that we're trying to beat. So we're going to optimize for high bandwidth cases. We need to match the kind of bandwidth that goes between modules on chip, and particularly to the IOs, because that's where we know we've got a lot of high bandwidth cases. And we want it to be not to add too much area. Okay, so that led to looking at a network on chip. Okay, so how many people here know what a network on chip is? Okay, so most people. Anybody here not know what a network on chip is? A few people at least. Okay, thank you, because there's several slides on it, so I'm glad I'm at least talking to someone. So I'm going to quickly explain what a network on chip is. I've drawn it here. There's two pieces of network on chip. Okay, there are links, which are just wires, right? It's just a bus of wires that goes between the routers. So the routers where all the logic happens. It's a complete interconnect in that it basically moves your data, it does the switching to get it to the right spot, and it'll buffer it for you. So basically the buffering is a form of the streaming data flow with back pressure. Like that style occurs all over the place. So that's what's used in these routers as well, is they basically have valid bits, they have back pressure signals, so they can say when the buffer is full, stop sending me data. So it's got distributed control to make sure it never loses data. Okay, so the way it works is, say this module here, module 4 has some data that it wants to send. It puts a header on it. I mean, there are a few variations of NOx, but the standard way you do it is you put a header on it that basically says, where am I sending it to? So it's the ID of some router where it's supposed to go. That's split into multiple units called flits. So flits are basically what can I send over one of these links in a clock cycle. Okay, and that's probably less than the whole packet, but that's fine. I will just split it up and I'll send it over multiple clock cycles. Yeah?
This is more so a question on the paper itself. From reading it, it seems to me like your mesh topology was the topology that's like most commonly experimented with. And I know there's like a mention about the butterfly topology that they remember, but I guess just from your recollection at the time, why was it only that a mesh topology was considered possible torus or?
So I like meshes. So you can see that's actually, I think that's actually the main reason, so to be honest. This is a mesh, right? So this topology, just for those who don't know, this is a mesh topology because every router connects to 4 neighbors. Well, let's forget the ones on the edge, but this router can talk to 4 neighbors, and that forms a two-dimensional mesh, okay? The reason I like two-dimensional meshes is the same reason as you go to island-style FPGAs. They are efficient to layout, okay? So you're basically saying, I can go a certain distance in a clock cycle. Let's make that the distance between our routers, for example. Let's put registers on both sides. The wires are nice and direct. This will go on one metal layer. This will go on a different metal layer. So it's basically layout efficiency. And now everybody has to adapt to it. Maybe my data, I have a lot of data going from here to over here. And there are other topologies. Maybe I could have the router here directly connected to that, and that might have been more efficient, and that would have been more efficient for that use case. But it is more difficult to lay out. So in an FPGA where I don't really know who wants to talk to whom, if I don't have that much information, it pushes me towards meshes because I know that they will be able to get the data everywhere and they are physically efficient. So it's kind of the same argument as like hierarchical versus island style. Does that make sense?
What I'm saying is, like, you could have had, let's say, just a torus where you connect the endpoints to each other.
Yeah, the problem with that is this, you can connect the endpoints like that. So that's a torus network, for those who don't know. It's a mesh, but you have wraparound links, so it forms a torus. I mean, this is a pain from a time enclosure point of view. So what they sometimes do is they'll do like some kind of folded torus, right, where they try to make it look more efficient. It still takes more wiring. So effectively, it's the reason that paper talks mostly about meshes is the fact that they are the most efficient to lay out. Does that make sense? And in a world where we don't quite know what the use cases are, we'll kind of line up with the island style philosophy and say, let's make it efficient to lay out, and then everything's got a layer on top of it. I can't prove that's the right choice. That is like an intuitive choice. Okay, so anyway, this data has been, put a packet on it, header on it, saying where is it going to go, broken it into flits, and then we send it into the NOC. So that module basically sends it into the router that's right beside it. And that animation is so cool that I'm going to do it again, right? So they go, one at a time. They can go right behind each other. So there you saw like a gap, but they can go right behind each other, and they go over multiple clock cycles through each of these routers, and they eventually wind up here. This router is a destination, so it looks at the packet header and says, oh, I'm supposed to deliver you to the module that I'm beside, and it does that. And then that module can throw away the packet headers and put this back together, and it's got its data. Okay, so that's how it works. So let's see, does this work well for an FPGA? Okay, so I've got a bunch of modules. They all want to talk to each other. These are their kind of big, high bandwidth connections, these blue arrows. So can I map that onto this NOC instead of onto a bunch of buses made in the soft fabric? Well, I can. So let's say that PCIe wanted to talk to one of these modules. It can do the same thing. Put a packet header on the data, chop it into flips, and send it off to, that module, actually I guess it's this module. This module can send it to PCIe, okay? So it can, and there was nothing special about what I just did. By putting a different packet header on it, it could have sent that data to this memory controller, could have sent it to, over here to the serial transceivers. So I can move data between arbitrary endpoints. And if I put a different design in, those modules are still going to overlap some of these routers. And just by changing what packet header they put in, they can send data to different spots. So it avoids that problem I had of hardening buses, where you just couldn't get data where you wanted to go because the endpoints were wrong. OK, so it looks good so far. But how do we build it? So a NOC is made out of a router, which does your switching, your buffering, your arbitration to decide who gets to go on the output links. And we need to build something that's different. Most NOCs don't have. We called it in this paper a fabric interface. It's basically how do we connect to the soft fabric, right? We want the programmable logic has to be able to get on this router. So we call that the fabric interface. And there are some proposals in the literature where people have proposed basically making a big FPGA that looks like a bunch, it looks like a bunch of smaller FPGAs, okay? So this would be like a regular FPGA. And then across some boundary, you would have to use a NOC. So we explicitly didn't do that. We didn't want any boundaries where you had to use the NOC. The idea instead is the logic goes wherever it wants to go. There's a few logic blocks that have been removed to make room for the routers, but you can just map your logic and your RAM and et cetera the same way you always have. And then you can choose to use a router or not choose to use a router, but there's no boundary where you have to use a router. It's like additional interconnect on top of the programmable interconnect. So that allows you to essentially be a little more adaptable. No matter what size your modules are, where they are, who they want to communicate with, you haven't kind of in advance constrained them to you must use the NOC only to cross this line, never to cross this line, and if you want to get from this half of the chip to this half of the chip, you have to use the NOC. So we explicitly didn't do that because I found that's really hard to use, right? Whenever you give somebody like this hard boundary and you say you must do this to cross this boundary, that's really hard for designers, and it's really hard for adoption. Like you suddenly have this point where people have to change their whole design style, and it's really risky. So this does not do that. Yeah?
Is it like designed to be transparent to the user, or do you have to use like an Avalon interface or something like that to set it up?
Yeah, it's not, I mean, that's a good question. So basically, so far, it's not transparent to the user. This fabric interface, effectively, you're going to talk to it like a FIFO. Okay, so you'd instantiate IP in your design that basically is, I have a FIFO interface. I can send data into this. So, and AXI is like a reasonable choice of like a standard interface. And so a standard interface is something that looks a lot like a FIFO. I can send data into it. I can read data out of it. But it's a weird FIFO where I send data in here with like an address saying where I want it to go, or a packet header saying where I want it to go, and it pops out over there. Does that make sense? And data, and I read from it, and the data I'm reading from it might have come from over here.
But in my design, in my Verilog, when I connect the two blocks with the AXI interface together?
No. So in your Verilog, you just basically say I'm talking to this AXI block, which is the NOC. like it's a NOC router. Behind the scenes, something else is also talking, maybe many things are talking to the NOC router, and it's up to you to write the logic to say this thing should send data to this ID. But no, you don't, in your Verilog, you don't connect, for example, this compute module to this PCI interface. They both instantiate what we call a logical router, right? It's basically kind of like a FIFO interface, and they're going to talk to that. And then it's up to the CAD tools to basically decide, I know that I'm supposed to use this fabric interface, up to the placement tool to decide where should I put this compute module and which fabric interface should I talk to. So that's essentially equivalent to like regular placement and routing, where you basically say, I know I want this LUT to talk to another LUT, but you don't say where they are. You just say, I need the LUT that is the ALU to feed the LUT that is the multiplexer. So it's the same idea. I want my compute module, which is like processor, to talk to some router and send it this data, and it's up to the CAD tool to decide which router it's going to use. Does that make sense? It actually makes you, essentially your placement becomes like a co-optimization. Where do you put everything to try to make best use of the NOC and the programmable routing? So that's a good question. Yeah.
What's stopping people from making the entire FPGA like network?
Well, so you could do that. And later in this talk, later in this lecture, I'm actually going to get to some things that effectively do that. It's no longer, you probably can't really call that an FPGA at that point. It's something that's still spatial. But if you take all the programmable interconnect out of the FPGA, like all the regular programmable interconnect out of the FPGA, you're not very good at like single bit operations, like some of the stuff where you're taking your lookup tables and doing fine-grained cryptography and network inspection and so on. You've lost the ability to do that very well. Does that make sense? If you don't care about doing that very well, you can take it right out, but what you have is no longer an FPGA. But you're going to see some examples of things just like that at the end of this lecture. Yeah?
How does the CAD tool estimate the timing numbers, like for example setup time or hold time, or even maximum product frequency? Because it's traffic dependent and it depends on the user.
So I'm going to answer some of those questions. Some of those I won't get to, but you can ask me after. Because there are other papers that we've written to talk about those things. I guess I have a short answer. You put registers here, okay? So your time enclosure from this compute module ends there. You get to that register, you're done, okay? All the paths through this fabric interface I'm going to show you actually has multiple registers in it. Then you go into the router. It has registers on its inputs and its outputs, sometimes in the middle. Okay, so there are no timing paths that suddenly just kind of go through the router and off wandering around. It will take you multiple clock cycles to go from here to there. But basically, if you've hardened the network on chip, all these registers have been built into the routers, and your time enclosure is done. Does that make sense? Like either or else somebody in IC design is in big trouble. But it's like it either works or it doesn't work. There's nothing that the end user can do.
But regarding the latest, there is some sort of...
Yeah, you do now have like a different latency depending on how far you go across it in clock cycles. So now that's where you need your placement engine to understand that it's desirable to keep that latency short. And you need the user to give you some more information about basically what we call traffic flows. Like the traffic that will flow from say this compute module to PCI Express. You say there is a traffic flow. I care about its latency or I don't care about its latency. It has lots of data traffic or has a little. So yeah, you do give additional information to the CAD tool, and it uses that to decide how important it is to get this compute module close to the same router close to a router interface that's near, say, PCI Express. Does that make sense? If it's not very latency sensitive and there's not much traffic, then it doesn't care much, and it'll optimize other things. If there was a ton of traffic and you said it was really latency insensitive, then it's probably going to try to pull this whole compute module down here so that it goes on the NOC and gets off right away. Does that make sense? And it'll do that while also considering everything else, right? At least in like the follow-on papers we wrote on this, like also considering what does that do to the rest of the programmable routing? Because usually this compute module is also connected to other stuff. So it also has to think about, is this a good idea or a bad idea? It's like a lot of trade-off. So good question. Okay, So, yeah, I guess I already talked about the no hard boundaries. And I guess I mentioned this, but this fabric interface is kind of unique to FPGA NOCs. If you build a NOC in a SoC, you know what you're connecting, right? Like you know I'm connecting a processor on one side and I'm connecting PCI Express or an accelerator on the other side. FPGAs are kind of unique of I know I've got a router, I'm deciding what to build, but I do not know what's on the other side. So you have to build a more flexible fabric interface that kind of anything can connect to. And you have to optimize your NOC for essentially many use cases, whereas in an ASIC you wouldn't have to. You'd know what your use case is. Yeah?
But even for ASICs, companies like ARM give you IPs, IP instantiated that you can make IDs by free NOC and then you can plug everything into it. And they have essentially like interfaces like these.
Although it's still done at the time you're designing your SoC. Like you could decide I want a 2x3 NOC because I know what I want to hook up to it. In an FPGA, you'll know how many DDR interfaces, for example, that you're sticking in your chip, but basically you won't really know what is this compute module. It's going to be like 10,000 different things. So you have this extra degree of like uncertainty. Okay, so the router in the study I'm going to show you is basically a full-featured router. This isn't a course on NOCs, but very quickly, a router has basically buffers on its inputs. So it's like the streaming data flow model. Data comes in. If you get full, you back pressure saying stop. Don't stop sending me data. So nobody loses data. They just get congested and slowed down. You might have multiple inputs. So this is a 5-port router, right? For a mesh, you have 4 ports coming in and going out to the cardinal directions, and you have 1 more to this fabric port to get you to the programmable logic. So that's 5 ports. So I got 5 different inputs. I've also got 5 outputs. In between them, I have a crossbar, right, to decide who gets connected to what. 2 of my inputs, maybe the south one and the west one might both be trying to send data to the east. So there's an allocator that decides who gets to use the crossbar, because I can't connect them both to the east. So they're going to have to, one of them is going to get buffered, the other one's going to get connected. And in this switch, we've used what are called virtual channels. So the virtual channels are to reduce the amount of blocking you can get in the network. We're basically building multiple buffers, for example, for the west input. Instead of just having 1 buffer here, we've got several buffers. And a packet will basically identify what virtual channel am I on, and that's which buffer it goes into. What this does is it reduces the amount of blocking. If some other traffic, if I'm blocked, I can basically still go into my queue. And if some other queue is full, it doesn't affect me. So it costs some area, but it makes your switch basically better at handling high load situations by having these multiple buffers on the inputs. Yeah?
Can you have like different priorities for the different virtual channels?
Yeah, so you can also do that. So, and there's a long time since I looked at the HDL for this one, so I can't remember. I think this one does allow different priorities, but that's the other thing you can do, is you might say one of these virtual channels is higher priority than the other. So, and in general, that is used for virtual channels. Okay, so, I mean, the exact details of this don't matter too much, except we're using a pretty both standard but full-featured routing architecture. Okay, so the first question we had is, well, should we harden this? Or maybe we could just build this out of soft logic, right? And it becomes like essentially an overlay, right? We'll just build it out of the soft logic. It becomes a design style, but we don't really have to change the chip at all. So we tested that with relatively narrow links, 32-bit wide links, and ran a bunch of experiments in 65 nanometers where we basically built this NOC, so it's hardened. And we compared it to Stratix 3, building it out of soft logic. And the reason we chose that is Stratix 3's area numbers for its basic building blocks are known. So we can actually do a proper comparison of what is the area of the hard NOC versus the soft one. And we did one in between. We did like a partly hard NOC, which means we hardened the router, which has got lots of logic and buffering and so on in it, but we used the regular programmable routing wires for the links. Right? So a NOC always has these 2 components, all the switching and logic in the router, and then the wiring that gets you to the next one. So we thought, well, maybe the wiring, we could just use the regular FPGA routing, and that might be okay. Okay, so if we do that middle one, basically we take out some logic blocks and we put in standard cell gates that implement one of these routers. And we also account for the fact that we have to have all the regular kind of crossbars and muxing and switch connection blocks to get signals into the router and out of the router to the programmable logic. Because this kind of partly hard one, it doesn't have any hardened links, right? It has to use the programmable routing to get to other routers. And the advantage of that, well, so we looked at how fast could you clock that, and if we made the routers not too far apart, we could clock it pretty fast, 730 megahertz. And it had the advantage of we didn't have to use a mesh. Okay, so because we're making the links out of the programmable routing, we can build anything, right? You can program the chip to make, this is a ring. We could make a butterfly network. This kind of network is sometimes good for data being broadcast or shuffled or switched. And we could just make weird topologies, right? Like we've looked at your design, or you as a designer have figured out that this is a good topology for you because that's who wants to communicate. And we could build all that because it's just being programmed. So this is more flexible. But it's also going to, it's going to chew up more of our programmable routing. And it's also, it turns out it costs us some extra area because we have to build more sort of input connection blocks and output connection blocks. So there's some extra muxing to make this work. So the other thing we could do is we could harden more. So the links between routers, we could make those out of just dedicated wires, and we get rid of a bunch of muxing, and we just have buffers now, right? Because we don't need those crossbars, et cetera. These are now dedicated wires that only connect us to the very next router. So it's kind of more like carry chains. So now I'm showing there's the regular routing channels, and we've added in these green wires. The green wires are like extra hardened wires for the links between routers. Okay, so it made it faster. So in this process technology, by dedicating the wires, we could run it faster, 900 megahertz instead of 730. But we now have to choose the topology. And we chose the topology to be mesh because it's going to be the easiest to lay out. And because, yeah, it seems like, it does go back to that other question. If it would be harder for us to justify this, right? Because we go, like, it's hard to lay out. We don't know who might use it, but maybe somebody could. Maybe you could justify something like this if you said, well, there are memory controllers down here, and we've analyzed their traffic pattern, and it turns out they want to do certain broadcasts. But it was very unclear to us that there was any pattern like that we could find. So we went for like physical integration. Okay, and so the area comparison was that there was a pretty big gain. So if we took the router, this pretty full-featured router is pretty big in soft logic. If we harden the router but leave the programmable routing for the links, it basically got 22 times smaller, and we could clock it 4 times faster. If we went all the way and basically hardened the router and the links, it got 27 times smaller because we get rid of a bunch of connection block muxes, and it ran faster, so 5.7 times faster than the soft logic. So both of these look like possibilities, but we kind of like the fully hard one better. Yeah?
So for the soft links, does the capsule make the decision of what topology to use, or does the designer?
That's a good question. We didn't go any further on that, so it could have been done by either. Right? If you went further on it, what you'd probably do is say the designer can tell you the topology, and then you can make a CAD tool to try to automate it. And that's probably when you have new features like this that's probably a good approach. You know what you're doing, tell me what you want, and I'll also try to build a tool to tell you. But we decided that hard looked better, like all the way hard, so we focused on that after this. Yeah?
So from a layout perspective, so you need 2 types of logic block layout, like the one without the non-wire passing through and so on.
Yeah, so we didn't worry about that, but you notice this is not a column. So we now would have to have logic block layouts, and we'd assemble those into columns, and then we'd have some spots where they weren't assembled into columns. So there's going to be a part here that's kind of a bit more unique. And we left that as an industrial problem of like, well, industry's got all the money in the world, just go hire more layout engineers. So But you're right, what we did doesn't fit nicely in a column. You don't have to keep things in a column, but there will be a layout cost, like some extra complexity. Okay, so let me talk a bit about flexibility for this. So I talked about we don't have any hard boundaries, like there's no, you can always get everywhere with the programmable routing still, so you don't have to use the NOC if you don't want to. And I talked a bit about we need this fabric interface to be flexible. So what does that mean? So we don't know, in an ASIC, you would know the clock frequency and the bandwidth demands of something you were connecting to the NOC. Right? Like otherwise you're a really bad ASIC designer. You're like, I'm hooking something up to this NOC, but I don't really understand what clock it's on, right? Like I really hope this chip comes back and works. Like the odds are not good, right? But in an FPGA, that's exactly what you have. The routers, one of the nice things about making the router, the NOC completely hard, right? So this case where we harden all of the routing links and the router is we can just close timing at the time you're building the chip and say it runs at a certain frequency. So in this case, 900 megahertz. And we can just say that's the NOC frequency, we're done. And there's a lot of efficiency that comes from that. So we actually wanted the NOC to run at one fixed frequency. So in this chip, it would have been 900. The future one, maybe it's a gigahertz. But all the modules that talk to it, we don't want to force them to run at that frequency. And also, they're not going to run at 900. So 900 would be a particularly bad choice because probably no designer is going to manage to make his or her design that fast. But we have no idea. And actually, you'll have different modules with different clock frequencies throughout the design hooking up to this. So we want this to have very little, essentially, glue logic. So we did two things. There's basically configurable time domain multiplexing. So this module could talk to, basically sends 128 bits of data. And that there's a configurable time domain multiplexing circuitry to basically say, well, maybe we're going to take, maybe you were running pretty fast and you were sending me data 64 bits at a time. So I'll mux that, two of those, I'll mux that 64-bit data into a double frequency 32. Or maybe you're running pretty slow when you actually want me to take four 32-bit numbers and mux them 4 times up in time to make a 32-bit output. So it's a configurable time domain multiplexing circuitry. You can basically increase your clock frequency by 2 or by 4. And the reason is to narrow the data, right? So we want to get to a narrower but faster channel. But there's still no reason to believe that this actually matches the router frequency. So then we go into a dual port FIFO that has 2 separate clocks and some logic to do safe clock domain crossing. So we can actually go from an arbitrary frequency here to an arbitrary frequency there. In this case, we're at 800 megahertz here and 900 there. We'll have some cycles where there's no data coming out because this side is faster than that side, but that's fine, right? So you'll have some bubbles where you just don't get data in. So this was actually important because we found, because the buses that you're connecting to these routers are quite wide, anything that you do in soft logic, and you could do a bunch of this in soft logic, it chews up area really quickly. By pushing everything you can into this fabric interface and hardening it, you make it much easier for design modules to hook up to it with very low soft logic usage. So that was one of the interesting things we found in this project. Okay. So yeah, so after putting these things in, it's basically easy to hook up to. You can get the full NOC bandwidth from your module. You don't have any restrictions on your clock frequency. Okay, I think I'm going to pause there. So maybe I'll take any questions, and if there aren't, we'll just go for a 10-minute break. Yeah?
Can we use some sort of clock gating for NOC clock to reduce power consumption?
That's a good question. You could. Yeah, you could. Let's see. Let me think about that. I guess the short answer is yes. I mean, on these links, if there's no data that's going out of them on a certain cycle, they won't toggle. Okay, so the router's built that, yeah, if there's no data for here, it'll just leave these alone, so you don't toggle. You could do clock gating on some of the logic inside the router as well. That's where you basically say, well, if there's no input data, like try to shut down as much control logic as I can. But the first order thing of don't change the state of these wires if there's no data already happens. Does that make sense?
Yeah, but this should be handled by the end user.
Not really. I mean, because that whole router is hard. These links are hard. This will be handled by basically the person designing the NOC. And I would say if you actually toggle these wires when there's no data, then that's fairly incompetent. Like that kind of stuff happens, but it's bad, right? Like you should just know, don't change the signals when you don't need to. To minimize the control logic switching is a little more tricky, right? Some things won't switch when there's no input data, but you might, depending on how you code your logic, you might wind up with having more of your control logic actually toggle than you might like. But that's all on the person designing the NOC to try to minimize how much it toggles. The end user is just going to send data in or not, and then basically the rest of the NOC will try to minimize switching. Does that make sense?
Yeah. And one more question: does the end user require to explicitly instantiate an IP core for talking with other modules, or?
You instantiate an IP core that is just your interface to the NOC. So think of it as like, it's a lot like saying I instantiated a FIFO or I instantiated an interface to DDR.
Yeah, but
Usually it's AXI format. That's what most companies have standardized on. And it's basically like you instantiate what we call a logical router. Like I will talk to this. It's not useful if you only instantiated one. Like if only one module talked to the NOC, it has no one to talk to, okay? So somewhere there should be at least one other module that also instantiates like a connection to the NOC.
but it's possible not to use this feature.
Yeah, you can just not do it. Just like you could choose not to hook up to like DDR. It's your choice.
And this is not managed by the captive, for example, automatically, or implicitly.
The basic answer is no. You instantiate it. Where I don't know how far Xilinx is probably the furthest along in commercial tools for this. They're not the only ones now with hard NOCs, but their tools are probably the most mature because they were the first company to do this. There's two ways to use it, right? So it's like HDL. You instantiate it. Another way is people use system integration tools. Okay, so like Xilinx System Generator, I think, is their system integration tool, and Altera's QSys. Those tools, you basically say, I've got a bunch of IP blocks and I want them connected together. So those tools can automatically put the instantiation of the NOC in for you. Because in a regular FPGA, they will automatically build buses for you. Does that make sense? So you can kind of do it at two levels. You instantiate it yourself, or if you're using a system integration tool, it could instantiate it. But you're not going to be able to just write a bunch of Verilog and say, you go figure out if you should change it to use the NOC. Nothing's going to do that. Okay, so let's pause there until maybe 5 minutes to. Okay, actually 6 minutes to. I want to claim back that one minute. Yeah.
Just one more question. So when you're instantiating the NOC, you have to like give it an ID because you have to tell it where it needs to go. And obviously in your design, you're gonna have a different amount of NOC, and you don't know where the router is gonna decide to place your things.
Yeah, you have to basically have like, see right. So there's going to be a step of like all the things that connected to the NOC. You're going to have to give them each an ID so you can like say, go to this one.
So that's probably an extra level of
Are we, Sahel, are we good? Okay, ready to get going again? I have like too many slides today. I'll try to go fast, okay? So I can get all the way to the end. Okay, so the previous results I was showing you, we were using a 32-bit wide NOC. That's what we did for the hard versus soft experiments, etc. And so the next phase of that research, we went, okay, well, let's just check that. How are we going to use that in some systems? And what we found is that actually 32 bits wasn't enough. So when we looked at like PCIe, DDR, basically the kinds of bandwidths that those were producing are 8.5 to 17 gigabytes per second, depending on which flavor, what version, etc. And Ethernet was a little lower. For 100 gig Ethernet, it was 12 and a half. But basically a 32-bit wide NOC at 28 nanometers would have given us 4.8 gigabytes per second if we clocked it as fast as we could, which I think was 1.2 gigahertz. And that didn't match the bandwidth of these key I/O endpoints. So we decided, well, it's going to be really hard to use because now you're going to have, say, 17 gigabytes per second of data coming out of DDR, and you're going to have to try to separate it into multiple traffic streams, send it to multiple routers. It's going to be kind of make design harder. Our goal with this hard NOC was to make design easier. So we realized we really needed to make the links wider. So basically one of the learnings from this research was start from the outside in, right? The IOs are where we actually know some of the bandwidth requirements. Make sure your NOC is sized so it can handle the bandwidth of those IOs without a bunch of effort, like without having to split it up into multiple streams that you put over multiple routers. So we changed the NOC for kind of the next part of this work to be wider, 150 bits wide, which gave us 22.5 gigabytes per second per link. And now that's more than enough to handle any of those I/O standards that I talked about. And that's just going to make it way easier to work with. You connect a DDR interface to like one NOC, and it can send data wherever it needs to send data. Okay, so we can match the I/O bandwidths. Once we made the links wider, our previous study, where well, initially we had been looking at having a relatively numerous NOC, like 64 routers. And once we made the links 150 bits wide, that looked a little expensive. If we cut the number of routers down to 16, then the area went down a lot to 1.3%. And in the initial studies we were doing for this, we were trying to keep the area really low because I think that's the easier way to get into an FPGA. So, for example, in Stratix 1, that was the first Altera chip that had DSP blocks. We only devoted 2% of the die size to DSP blocks. And that still actually gave us a lot of multipliers, but it was in that first generation, most people didn't use it because it was new. And they were used to not doing multiplies. That user base wasn't yet on FPGAs, or they knew all sorts of tricks for soft multiplies. So I thought, well, if we make it cheap enough, it's easier to sell to companies, basically. You can put it in, it's a bit of a tax if you don't use it, but not too high a tax. So I guess we switched the NOC at this point from many nodes with relatively narrow links to let's have fewer nodes with wider links. That's going to be easier to use without blowing our area budget. Okay, so that was the NOC. Yeah.
Was there kind of a challenge if you reduce the number of router nodes that you're not going to be able to get enough data to match the bandwidth increase?
If you reduce well, there is a cost to reducing the router nodes. We're not going to get as close. Like we can't have as many modules hooking up to this, so we have lost something. But we just decided that it was acceptable, right, to keep the area down. Now, if you said this is not enough routers, I want to have them more evenly distributed in the chip, you could double the die budget and say I'll build 32. You could triple it, etc. So there's no real hard answer to this. But we thought it was probably for the next set of architecture research we did, it was better to try to keep it small. But not by keeping the links narrow. We thought we had to go the other way. Does that make sense? Yeah. There definitely is a trade-off there. So, okay, so where should I use this NOC? Okay, so a NOC has variable latency. It is basically like that streaming data flow style. You've got valid bits, you've got back pressure signals, things are getting registered. There can be contention where you don't get through the router right away. So we can't just put it in between two blocks of logic that expected a fixed latency, right? That's going to break. So where do you think you always have variable latency in a design? Like, where's the first place you should be used? Yeah.
I guess you can have variable latency. Like when it's like a stream data flow, it's not like a hard requirement, like it's going to be scanned.
Yeah.
I guess if you have something like
Yeah, and that's exactly our thought too. So if your whole design streaming data flow, then you're solid, right? Like a NOC can sort of be dropped in because you're already dealing with variable latency and your design will be robust. But there are lots of pieces of logic that aren't designed that way, but they have to be that way around the IOs. Okay? IOs are fundamentally variable latency. So we want to look at how can we use this near the IOs. So like if you talk to DDR and you assume that you're going to get an answer in exactly 120 clock cycles, your design will never work, right? Because that will never be correct. There could be a pre-charge event. I mean, in real systems, you'll have competition for the DDR controller. So often this is not just you talking to it. So that's your first problem. Second problem, all sorts of clock domain crossings. So you could be up or down by a couple cycles. Third problem, the DDR chip could just do a refresh right when you ask for it. So it's madness, right? If you didn't already have sort of ready valid signaling talking to DDR, your design's already broken, so you're a lost cause. So if we put that traffic onto a NOC, we don't need to do any re-architecting. It's for sure got ready valid signaling, so on. So so we wanted to see, okay, let's take that use case, and we want to talk to a DDR controller, because most designs have DDR in them. And we can build that using like a system integration tool. So Altera's system integration tool is QSys. So it basically builds buses and arbiters and so on, like soft buses for you. So you don't have to build them yourself. So we did a study where we took a bunch of modules and had them share one DDR interface. So they basically need to build soft buses with pipelining, multiplexing, arbitration. And if their clock frequency is not a multiple of the DDR frequency, they also have to have like that 2-clock FIFO, like what's called an asynchronous FIFO to safely cross the clock domain. So we could do that too. And then we compared that to what if we take the same system, but we just have a bunch of modules, and they're going to use a hard knock. And the hard knock in this case was, we kept switching the link width, so now it's 128 bits. So I don't know why I told you 150. We did 150 briefly, but this still is enough to carry all the bandwidth of a DDR controller. So it needs to be beefier. Does that everybody clear on that one? Okay. Okay, so how efficient is this? So we're just talking to one DDR. So we're actually not using all the capabilities of the NOC, because we've actually built a NOC with, this is actually the exact NOC. It's got 16 routers. So we could hook more than a single DDR controller and a bunch of modules up to it. Its area is basically fixed. We built the whole thing, and we either use it or we don't. But that's what it's going to cost us. And it doesn't matter how many modules we hook up to it. In this case, because we're hooking up a bunch of modules and they're all talking to one DDR controller, it's not enough to actually congest the NOC. But in any case, it's not going to affect our area. And in this case, it's also not causing congestion, so it's fine. With QSys, as we hook up more and more things to that DDR controller, we need more arbitration in the soft logic, so more LUTs, more muxing. Things get further apart, we need more pipeline registers. So the logic area is going up, okay? And because we know the area of a logic block, we can actually plot these on the same axis. This is like silicon area in both cases. Clock crossing is actually pretty expensive because these buses are fairly wide. So when the modules are not on a multiple of the DDR frequency, hooking them up is quite a bit more expensive. This is why that fabric port was pretty important in the NOC. Absorbing that clock crossing logic and time to multiplexing logic is a big win. So anyway, the takeaway from this one is that the hard knock pays for itself pretty early in terms of area. If you had one module talking to DDR, then that's cheaper to do in soft logic than a hard knock. But once you get up to even 3 sharing a single DDR interface, you've already paid for this knock. If it's actually one module and you have to cross clock domains, it's almost the area of the knock. So it's pretty area efficient. And you could hook quite a bit more up to this knock, right? Like it's not saturated. If we did the same thing, but now for power, it looks even better. So the hard knock, basically its power didn't move very much as we hooked more things up to it. The reason is the traffic is throttled by the DDR controller, and we're always saturating it. So even though we've hooked more things up to the knock, the amount of traffic is still constant. It's just whatever one DDR controller can do. As we hook more things up to soft buses, the power goes up because we've got more pipeline registers, more muxes, it's going further. And for power, the knock looks quite good. Yeah?
When you say hard knock, you mean the entire network, all the routers, everything?
Yeah, this is like a 16-node knock. So all the routers, all the buffering, all the connections to the links. We're basically taking the areas, we're assuming we can fit the metal for the links basically on top of or in between the FPGA wires. So it's basically like the logic area and the router area. Does that make sense? So again, it looks quite good for power. We also looked at, well, how does this work with like data center FPGAs? Where we're basically looking for like cases where this looks good, okay? So in data center FPGAs, like what Microsoft does for Catapult, remember they have this shell where they've locked down some of their logic to interface to the IOs and do some housekeeping. And then they have this region that they call the role where they can put in, like, what do I want to actually accelerate, okay? And these shells can be fairly expensive. So in the first catapult generation, it was 23%, and it went up into the 40% range in the second generation of catapults. So they can be pretty big. So part of what makes these shells expensive is you have to kind of compile the shell and lock it down in advance. That's what's giving you productivity. You've kind of placed and routed it and closed timing, and then you lock it down and it never gets touched again. But that means that it's brought signals to a certain spot on the periphery of this roll, and all the rolls you might put in there kind of have to live with that. So when I compile this roll, it has to just get signals from wherever the shell hooked them up on its periphery. And if I put a different accelerator in there, it's just got to live with that. And a lot of these rolls won't even use all these interfaces. So we essentially have to over-engineer the shell. We have to make sure that everything that any one of our rolls would want, that we bring that to it. So we're going to tend to over-engineer it for like what's the worst case. And when we compile our accelerators, they're kind of constrained a bit more. Like they have to make sure they route signals to wherever the shell brought things. Place and route engines can do that, but the more you constrain a place and route engine, you're just making its life harder, right? Like it has flexibility to optimize other things when you say, make sure you bring this bus to here, that bus to there, and so on. So if you have an embedded NOC, basically your shell gets easier. Your shell gets easier because before I was essentially building a bunch of parts of soft buses and locking them down to get things to the edge of the roll. And now the NOC will do that for me, right? It'll bring data right into the, and it doesn't just bring it to the edge of the roll, it brings it throughout the roll. So it's less constraining for the placement and routing of the roll. And I basically didn't have to build these soft buses out here. Okay? And that gives me some interesting options too. Like I could put multiple smaller accelerators in, and they could all still get access to the data because the NOC kind of brought the data everywhere. It didn't just bring it, or it gives access to the data from everywhere, not just from one spot. And we did some studies of what is the impact of those two, like on routing congestion of these styles. So this is from a sample design that is basically compiled flat. So it means you compile everything. There's no shell, no roll. You just take the whole design and compile it. And the red is bad. That's routing congestion. Then we took that same design and basically divided into 4 rolls and a shell. Okay, the shell's bringing in the DDR and PCI Express, et cetera, and its routing is locked down. And then the 4 rolls, which all were in here too, have to be compiled in their regions. And you get a lot more routing congestion. Okay, and it's because of the fact that the place and route tool can't optimize as much. We had to pre-route these buses. Maybe we didn't put them in exactly where we'd like. Maybe some of them are going places where they didn't need to go, but we can't reclaim the routing, but we get a lot of red. And if we basically model routers that bring data in for us to the rolls, we get rid of the vast majority of this congestion. Yeah?
In the last image, what is the routing hotspot answer one corner?
So why is this red?
Yeah.
It's actually, there's a DDR interface over here, and the wires for that DDR interface are being dragged across the roll to get into these routing ports, which are part of the shell. So if we had we didn't model this, but basically, if we had that DDR core have direct access to the NOC, like basically have a router built right into it, then we wouldn't have to drag these wires across, and we wouldn't have this red. And that's probably a more logical way to do it. But we're doing these studies by basically floor planning things within Cordis. That's what, so we couldn't directly model that. We could just comment that would be smarter. This is like a regular mesh. I guess that's like moving away from the mesh in a sense, right? Like we know that that DDR core is going to be a hotspot, give it its own router. Does that make sense? Okay, so what about interposers? I talked about interposers. I just have one slide on that. So I told you that one thing to worry about with interposers, although it hasn't been catastrophic so far, is if these micro bumps don't scale as fast as the regular wiring, we might wind up with essentially a reduced ability to get wires across the interposer. And if we get a smaller fraction of our wiring across, our CAD problem is going to get harder. So NOCs are actually they're actually nice with interposers. The reason they're nice is one of the ways you deal with, I can't get enough signals across some spot, is you can time domain multiplex, right? And a NOC already time domain multiplexes. You basically build a hard NOC, you're going to run all these links at the max frequency that you possibly can forever. So, for example, 1.2 gigahertz is a pretty reasonable frequency for a hard NOC. You put data onto this router and it comes out there. Where it crosses the interposer, it's actually running at 1.2 gigahertz. So it essentially naturally gets you more bandwidth for the same amount of wires. You don't have to only use the NOC, but basically the wires here are more useful in terms of bandwidth, right? They're all running faster. Yeah?
I guess, just a question about NOCs in general, and I guess maybe with how routing the FPGAs, and I'm more so thinking about it with mapping and CJs, just because that's what I'm recent. Would NOCs be able to route sort of any type, just because of the fact that they are naturally trying to resolve deadlocks? I guess another reason to use NOCs would be that you don't have to worry about routing anything, just because, let's say, they can route anything. Sorry. Moving flits around in certain directions based on congestion or whatever it is. I guess, is that one of the other reasons you use NOCs?
I mean, so that was one of the first strings I gave, is they can get things from anywhere to anywhere, right? So doesn't mean they won't have congestion, you're right, but they're a good thing to harden because of the fact that they're flexible enough after you've hardened them to get data from anywhere you want. I don't know if that fully answers your question or not.
I guess in a sense, because you wouldn't have to worry about the routing structure.
I mean, you still have to route, you still have to worry about it. Like, you still have to think about, like, how do I move? You want to be efficient with the NOC. The NOC has a certain amount of bandwidth, just like the FPGA has a certain amount of interconnect. So if you take everything that's going to communicate over the NOC and you put it as far away as you possibly can, then all your data has to go through, this thing has to go to here, so it has to go through all these links. This thing has to go to there, it has to go through all these links. And I repeat that. It's like a worst case bandwidth pattern, right? And I'm probably going to wind up with, if those things are moving a lot of data, the time domain multiplexing will work, but it will slow down. They will all be waiting for each other. So you still have an optimization problem. If you can basically have the routers move data shorter distances, you can get more overall usefulness out of your, overall utility out of your NOC. I don't know if that answers your question or not.
I guess it does, yeah.
So anyway, this was another reason I thought NOCs were good. Xilinx has now done this too. So in their Versal devices, one of the things I've seen in one of their recent presentations is the NOC wires are some of the wires that cross. So they are finding that they've got to be clever about how to make maximum uses of the limited wiring demand, and the NOC wires get priority for this exact reason. So all the NOC crosses because it's fast, gives you the most bandwidth for a given number of wires. They don't only have the NOCs crossing, they're able to get other wires to cross too, but they give these ones priority.
I guess with bus-based routing, you could say, like, let's say PNR because your design can do that.
Yeah.
Could that ever be the reason of, like, PNR failure, let's say, if you have a NOC?
You shouldn't fail PNR because you should just slow down. So it should have more, it depends how you build your NOC. But for the NOCs I've been showing you here, you wouldn't fail PNR. You just get more congestion if you overuse the NOC, and things would slow down. Which is, you're right, that is a desirable thing to have. It's not desirable to slow down, but one of the things that's a bit annoying about FPGA compilations sometimes is like the all or nothing. Like when it doesn't work at all, it's difficult for you to go into the lab and improve or get a prototype. Yeah.
We saw some power graphs a bit earlier. I was just wondering, we saw that like the NOC is essentially always running at 900 megahertz even if the designs are slower. And that still doesn't seem to impact the power?
Well, you only toggle when you have to though, right? Like when you run at 900 megahertz, there's only a limited amount of control logic that's actually running at 900 megahertz all the time. all your data, if there's no data to send, the links don't toggle. The buffers don't toggle, the switch doesn't toggle. Does that make sense? And toggling is energy for CMOS. If it doesn't toggle, it doesn't matter for dynamic power. So, okay, that was all academic stuff, but it's been adopted in commercial chips. So let's talk about a couple commercial chips. So Xilinx is the first commercial chip that put a hard knock in. It's very close to what I just showed you. These are the routers, okay? These are the links. The wires are the links. This shows it like there's a gap in the programmable fabric, but there isn't, right? All the programmable wiring wires continue. So again, there's no hard boundaries. They used 128-bit wide links at 1 gigahertz, hardened both the links and the router. And the reason for this was, again, to match the DDR channel bandwidth. Okay, so one of the key use cases, probably the most key use case for the NOC, is take data from memory controllers. So they made sure that the links were wide enough and fast enough to handle that. This might not look like a mesh, but it is similar to a modified mesh. They wanted to keep a column-based layout. So I showed you what the plots I was showing, we didn't have a column-based layout anymore. What Xilinx did is they basically took the routers in a mesh and they pushed them into columns vertically, and they pushed them down. So basically they wind up with a bunch of wide links at the bottom for their horizontal part of the NOC, some wide links at the top, like extra links. So there's basically like 4 sets of routers all in a row, 4 sets of links all in a row, all 128 bits, and then 2 at the top. So that's to give you more horizontal bandwidth. And then they basically put 2 columns of router here so they can stack them on top of each other. Okay, that's to make the layout easier. So it's kind of like you took a mesh and shoved things over here and down here, but it's kind of as close as they could get to a mesh while maintaining a column topology. And they actually have quite a few routers. So depends on which chip it is, but they can have like 100 access points to the NOC, like fabric ports in one of their bigger chips. And they have a fabric port that does all the clock domain conversion and so on, like I showed you. They went a little farther. They said that's the only way to access the memory controllers. So you have to use the NOC if you want to talk to DDR. They didn't even bother building a programmable routing one. So overall, pretty close. But we presented our results at Xilinx, and Trevor Bauer, the lead architect, told me that it was like very close. So they adopted that. But I think I've mentioned this before. The one thing they said we got wrong was we said that it doesn't look that hard to fit the link wires in. They said that was much harder than, so they said that we missed that one. But anyway, they fit it. Altera, Acronix is another FPGA vendor that has hard NOCs, but I'm not going to talk about theirs. They use a somewhat different topology. Altera's most recent FPGA, it's called Agilex M. Okay, so that's a certain subgroup within Agilex has a NOC. And it's interesting. So basically the Xilinx one, you can think of as being very close to the micropaper, right? Pretty general purpose, pretty close to a mesh. Optimized for traffic to DDR controllers. The Agilex one is different. It's optimized for access to high bandwidth memory. So this Agilex chip has a high bandwidth memory stack at the top, high bandwidth memory stack at the bottom. Okay, high bandwidth memory, once again, is a stacked form of DRAM. So you could take, say, 8 DRAM chips, stack them up. They're on a silicon interposer, very wide data bus, very high bandwidth. So it is DDR, but it provides much more data bandwidth than a single normal DDR channel. So you've got 1024 IOs running at 1.6 gigabits per second at the top and again at the bottom. So that means 410 gigabytes per second for like each of these interfaces. The interface is physically distributed. Like there's no way you can take that data and get it into the FPGA fabric. So it distributes that data. But it's a natural case for a NOC, but it exceeds the bandwidth that this Versal NOC can handle, right? These links can only handle like a fraction of that bandwidth. So Altera built a custom NOC that has wide horizontal links at the top and at the bottom. And then they built vertical unidirectional links. So Going into the FPGA, you actually can only go in. You can't come back out on the NOC because there's usually more read traffic from an HBM than write. So they were trying to optimize for read traffic. So they put a whole bunch of bandwidth to move it along the top, and then they put dedicated bandwidth inwards to move the read traffic in. And those vertical links basically connect into the M20Ks, so the RAMs, and a bunch of them, like 20 of them vertically stacked, to use them as essentially a distributed FIFO to spread out the data so that it can connect to the programmable routing. They haven't ever published a paper on this, so this is kind of from mining some of their data sheets, so I can't really give any further information beyond this. Maybe some of your classmates who are from Altera, you can try to like squeeze for information. So anyways, it's quite interesting. It's but yeah, it's a different approach. They built essentially quite a customized NOC to solve sort of this one case. If you're going to send write data to the HBM, you send it using the regular programmable routing until you get up here. So it's like asymmetric even. Then you get onto the NOC closer to the edge. Yeah.
So if you want to read from the HBM, you have to do it from the M20Ks?
Yeah. So at least using this NOC, and I believe this NOC is like I didn't read carefully enough to see if they can use the programmable routing directly or if you have to use the NOC. But if you use the NOC, the idea is it distributes it into the M20Ks, and then you read out of the other port of the M20Ks. So it basically avoids routing hotspots too, right? Does that make sense?
And the M20Ks kind of act like, I guess, caches.
Yeah, and they're kind of like part of your FIFOs. Like you have naturally FIFOs as the ingress and egress of a NOC anyway. And you have this problem with this amount of bandwidth of you've got to kind of spread it out so it doesn't create hotspots. So they use the M20Ks to sort of solve both problems. So I'm going to get like a FIFO and it's going to be highly distributed. So, yeah.
So does that mean if I use the HBM memory now, I have a bunch less VRAM to use another time?
If you use this. Now, I haven't read their documentation closely enough to see must you use this or is it your choice? Because there are trade-offs, they may have made it, like Xilinx said, you have to use it, right? Like we're not building a regular interface to DDR. I don't know if Xilinx, if Altera said you must use the NOC or if it becomes just an option. The safer thing for them to do would say it's an option. But the reason they would have built this is the fact that you're just getting tons of, like HBM provides tons of data bandwidth, and not having a NOC doesn't make your problem go away. Like you just have tons of congestion in your programmable routing. You have all the problems I talked about earlier. And you're going to have a bunch of memories chewed up for buffering as well. So yeah, not using it doesn't make your life suddenly all butterflies and songs. I don't know if anybody here from Altera wants to add anything to that. So I don't mean to put you on the spot. Like I don't, but if anybody's like, oh, you got that wrong and that's the way it works, feel free to interject.
I don't think we have any like knowledge about how HBM
Okay. Okay, that is it for NOCs. And so on to the next thing. Okay, bus-based routing. So the last part of this, I'm going to start going through a bunch of things that could be called CGRAs. CGRAs are coarse-grained reconfigurable arrays. Is like a really broad catch-all term. So I'm going to talk about a few things that are kind of, you could think of variations on FPGA and spatial computing or forms of CGRA. So and they're kind of going from less radical to more radical. Okay, so bus-based routing is one of the less radical things. The idea of bus-based routing is most of a design is multi-bit quantities, right? So you can't chew up the huge amount of routing in an FPGA with just all 1-bit buses. You got lots of like 128, 256, 512-bit buses. But we route every bit individually between the LUTs or the DSPs, et cetera. You know, they all have individual SRAMs controlling them and so on. So maybe that's inefficient. Maybe we should just route entire buses. And what we'd save is SRAM bits because we wouldn't need as much configuration to control. We could have SRAM bits that control the whole bus, not just like an individual set of wires. But our cost is that we may waste some of our wires and switches because, you know, if we built an FPGA where all the routing is 8 bits wide, we still have some 1-bit wide control signals. We might have some 12-bit wide buses. We might have some 17-bit wide buses. So we're going to get some wastage there where the bus width doesn't quite match. So this is a paper by Yi and Rose from a while ago. But they basically looked at bus-based routing in an otherwise conventional FPGA. So the only thing they changed is they added in bus-based routing. Okay, so let's see if I can show this. This, I guess, is the key. So this is just a regular switch block, like an FS equals 3 switch block. But normally I'd have a bunch of SRAM switches that control individually each of these switches. And that way I could connect this wire to this wire, and I can connect this wire to go to the right, and I can do anything I want, right? So they said, well, no, we're not going to do that. We're going to remove a bunch of SRAM cells so that there's just one set of SRAM cells that controls all of these switch points. And what that's going to do is that these 4 wires are going to work in lockstep. They're going to work as a bus. So if you come in from above and you want to go out to the left and you want to go into this logic block, every one of those decisions will be made like 4 bits at a time. And because I only built you one set of SRAM. I didn't build you four sets of SRAM, I built one. So every one of these has to follow the exact same path. Does that make sense? And they found, I should have stopped and said who, okay, see if you actually saw that quickly. Do you think this had good big gains or not? If you could read quickly, you already know. Okay, but we'll see how fast you can read. Okay, so it didn't get very big gains. Why do you think it didn't get very big gains? Yeah.
I think maybe because SRAM doesn't use that much area. Like you're saving on SRAM, probably you're not saving that much because SRAM is pretty well area optimized.
Yeah, so that's actually the most fundamental reason, is like they're kind of bound by what is the amount of SRAM in this chip. And in a typical FPGA, it's maybe 25% of your area, so it's significant. Maybe it's 30. But that's like an upper bound on what you can save. They're not actually removing any switches. So I can't save switches, I can't save wires, I can only save SRAM. There's an upper bound on that. And I'm also going to lose, well, you said didn't give it away here, so that's good. Yeah, go ahead, Alex.
What would you lose is that if you actually go back to the bigger picture, let's say this is the bus-based solution. Let's say I'm now going to do the non-bus-based solution with the prior FPGA approach. It's either going to get this solution, or if your router is very good, it will find another solution which is close, but it's going to be slightly better in wiring or some other metric. So you're just constraining the problem more.
Yeah, yeah. So you are more constrained. It could make the router get a worse solution. Yeah.
Wouldn't it be like the COE size get slightly smaller? Because you're not, like the connection, like the input blocks, the output blocks.
Yeah. I mean, this gets smaller too, right? Like this is kind of like your input connection block also is sharing SRAMs. But it's the same idea. It's sharing SRAMs that can't share muxes. You can only share the control. Does that make sense?
So I guess what I'm asking, what I'm thinking of is like if you have 16 inputs going into the COD, you need to like do all the cluster stuff inside.
Yeah, I can't remember in this one if they had a crossbar or not. They would basically, you could control the crossbar in the same way. You're saying maybe you can remove some routing flexibility. Like,
Yeah,
I think.
you would have like a 4 crossbar inside because like it's a bus. So
Yeah. I don't know, that's a good point. So they didn't start changing the routing flexibility. So that puts a limit on what they could save. But you're right, maybe you could change the routing flexibility and maybe you could get bigger gains there, but they didn't investigate that. So yeah, so the biggest one is only saving SRAM. Basically the bus width doesn't match the design. So they chose a 4-bit bus. And they found that there's always some stuff that's control logic or weird. So they made only half the wiring bus-based and the other half they left 1 bit. Even when you have a bus, you can have irregularity. So you might have a 32-bit bus, but maybe the top bit is a sign bit, right? Well, from the CAD tool's perspective, that's not the same. That's not a 32-bit bus. That's like 31 bits to do one thing and 1 bit that's different. So anything that's a little different, you can't follow this. So it's pretty easy to get little irregularities. To save the most SRAM, you'd want to make this bus really big, but then you have the most risk of wastage when something doesn't fit that. Like if you made a 32-bit bus, even 32-bit quantities might not fit in it if the top bit was weird. It was like a sign bit that was processed differently and so on. So I guess, I think Amir kind of hinted at this though. Maybe larger gains are possible if we change things more, okay? So, and what coarse-grained reconfigurable arrays do is they use bus-based routing. So they say, okay, we're optimized for larger data operands. So either most or all of our routing will be like bus-based. And then they also say, okay, we're also going to make the function units more coarse-grained. We're not going to use LUTs as our primary function unit. We'll use, say, ALUs, because that can also save us some area. And then they generally have limited routing flexibility. And the reason a seizure array generally has limited routing flexibility is, yeah, you just can't save enough if you're only taking SRAM out. You got to start getting rid of switches. And that's an interesting trade-off, right? So that's where you have to go to get big gains, but it can make seizure arrays hard to route, all right? So it changes your design space a little bit. Okay, which leads me to seizure arrays. There's tons of seizure arrays out there, so I'm not going to try to be comprehensive at all here. I basically picked commercial ones because I thought it'd be interesting to talk about ones that, have a commercial variant. But yeah, there are totally way more seizure arrays. Don't be offended if I don't talk about your seizure array. Okay, so the first one I want to talk about is, I guess, a seizure array that I would call sort of a classic seizure array. Okay, this is a seizure array called plasticine, and it was published in ECE 2017. And one of the things that's interesting about it is actually it was commercialized with a bunch of enhancements by Samba Nova. So who's heard of Samba Nova? Okay, so a reasonable number of people. So Samba Nova makes machine learning accelerators, and they use a seizure array, and that seizure array is based on plasticine with a bunch of enhancements. Okay, so Samba Nova doesn't publish a whole lot about what's actually in their chips, so the most information I can get is just go back to the academic paper that started it. So this is what plasticine looks like. And it's a little complicated, so let's see. Basically, if you think about it from how did I get here from an FPGA, the logic block has turned into things they call PCUs. And I think PCU is like the programmable control unit. Okay, so this is like a coarse-grained block. It's not LUTs, and it's not optimized to work on 1-bit quantities. It's actually 16-way SIMD. Okay, so it's optimized to work on bigger operands, not single bits. It's optimized to work on like 32-bit operands, and not one operand, but like vectors, 16-way SIMD. And then inside this PCU, I'm going to show you in a minute, it actually does 6 stages of operations. So it's got a little programmable pipeline, basically. And that programmable pipeline is like configured like an FPGA. So you tell it what you want it to do, and then it does that. But what it wants, so you program in SRAM cells. But what it's doing is 32-bit operands in a certain cascade on vectors. So pretty far away from doing individual LUT operations. Okay, then the block RAMs that we have in an FPGA basically have been replaced by these programmable memory units, these PMUs. And those are basically 16, like a 16 grouping of 16 kilobit block RAM with some control. Okay, so again, it's optimized for a bigger granularity. So it's not like a single block RAM, it's 16 of them. It does have some bit-wide routing because it needs that for control. It has some 32-bit bus-wide routing for 32-bit scalars. And it has some routing that is optimized for 16 element vectors of 32-bit numbers. Okay? And that's what's in these S's. Right? This is basically, there's some routing inside these PCUs that you're going to see, and then you've got these S's that are your other routing to go between your PCUs or your logic blocks. And they put registers in these switch blocks. So it takes you multiple clock cycles to get through a PCU. It takes you multiple clock cycles to get through the routing to the next PCU. Does that make sense? Okay, so here's what the PCU looks like. So again, this is like their logic block. So I've got 16-way vectors coming in here of 32-bit numbers. And I've got a control block here for single-bit processing. And I've got a scalar block. So I basically bring in 16-way vectors that go into these vector FIFOs. I got a scalar input that's a 32-bit number that comes in here. And I've got some individual 1-bit numbers that come into my control block. And then it basically goes through a pipeline. So there's a pipeline of function units that can basically be configured to do various functions, but these are basically programmable ALUs. with this pattern of routing and registers in between them to allow them to be fed essentially in a cascade, right? And it's not just a linear cascade. You know, this one can send data to this, this functional unit, to this register, to this functional unit. But they can also do some things like feedback to do more complicated processing. So from these registers, I can go back. I can bypass this functional unit with some data. I can send some data to the registers above me so I can do fan out. So yeah, it's a pattern that they decided matched a bunch of data flows that would be interesting. I can feed data forward, I can feed data back, I can start shifting data over or broadcasting data out. And then on the other side, I get basically the same volume of data. I get some scalar outputs, I get my vector output, I get my control outputs. So 1-bit wide, 32-bit wide, and 16 times 32-bit wide. Does that make sense? So awful lot bigger than a logic block, right? Like there's a lot of processing that happens inside of here. So you can read the ISCA paper if you want to get all the details of it. So the results, they compared it to a Stratix 5 FPGA on 13 compute kernels. So it's not like appropriate for bit processing, so they focused on compute applications. And they report like a very big gain. So 1.6x to 77x power performance gain. So, so it's like power per throughput, basically, like energy efficiency. But there's pretty big caveats on that. So I would take this as a number not to exceed. The first thing is that all of their applications are 32-bit floating point, and Stratix 5 didn't have hard floating point. So this number would look probably quite a bit different if they went to like ARIA 10 or a future FPGA that actually had hard floating point. And obviously, other applications with smaller bit widths are probably also going to play better on the FPGA, right? Like this is kind of a great match to the fact that they've built 32-bit floating point units. In comparing to the FPGA, it's always hard to compare really disparate devices like this. So what they did is they have a custom hardware flow that is used for their CGRA. They also use that same hardware flow to generate the FPGA HDL. So it's a reasonable thing to do. It's a lot of work to do this, but it leads to the question of like how optimized is that, right? Because that flow was actually built to generate, for their CGRA, is now generating FPGA HDL, which was not its primary purpose. So it's not clear how good it is. Their biggest gain came out on a CNN, where they got a 77 times energy efficiency gain. But I mean, CNNs are not normally run in 32-bit floating point. Nowadays, they are normally run in 8-bit, sometimes less than that. And so you wouldn't really run this in 32-bit floating point, certainly not on an FPGA that doesn't have 32-bit floating point. So optimized versions of CNNs do very well on FPGAs. So anyway, so the very big gains, but I'd say there's like quite a few caveats to keep in mind for that. Samba Nova has commercialized this. I've talked to Kunli, the founder, about plasticine. He said one interesting learning that they had was that it had to be more dynamic in Samba Nova, meaning they had to reconfigure a lot more often. They had to get the reconfiguration time down. So that's interesting. Basically, this is FPGA-like in that you configure it, and it does one thing for a long time. And they had to get that configuration time down because they found even in machine learning applications where there's a lot of regularity, you still have to switch more often than you might think. So that's kind of an interesting learning. Samba Nova, if you go and look at their website, you'll find that they're building hardware, but they talk a lot about their full service ML stack, which runs on their hardware. And they talk a lot more about that than the details of how their hardware works. It's much harder to figure out how the hardware works. So I think that may indicate that their programming model is challenging, and a very reasonable response to that is to say we're going to try to go a bit higher in the stack, right? We will program this for you because it's maybe a bit difficult for the average person. Now I'm guessing, right? But that is often a challenge with these unique CGRAs, that it can be difficult to map applications to them. Yeah.
Why are they using CGRA in the first place? Why not ASICs or why not anything?
Well, I mean, a CGRA is an ASIC. In a sense, everything's an ASIC. Do you know what I mean? Like, Like an FPGA is an ASIC, a CGRA is an ASIC too.
Then my question shortly, the reconfigurability is there for different machine learning models or something?
Yeah. I mean, nobody builds, okay, so there is actually one company, one of the founders of TensTorrent has actually Lubisa has created a new company whose goal is to make an ASIC for one machine learning model, okay? That is a unique business strategy, which he knows. He says this, he's doing it, TensTorrent was configurable, now he's gonna do something different, he's gonna do it not configurable. The reason it's unique is when you talk about there's an ASIC for machine learning, virtually, with the exception of that company, people normally don't make like an ASIC for like this exact machine learning model, right? They build in enough programmability that at least if you change the model within a certain range, it'll be okay. Does that make sense? So I guess that's what I mean by Samba Nova. They've never published it. Presumably they're continuing to evolve the architecture to give it what it needs for machine learning. But that's not as specific as you can just hardwire everything. Because literally you could like 3 weeks later just go like a new model came out and like my ASIC is like, I should put them in Lucite and put them on keychains, right? So.
Also, like, I also, like, this thing about full ML stack, I think Cerebras also does this, right?
Not as much. When I say full, so Cerebras actually, which I'm going to talk about in a minute, but basically you can just run on their hardware in the cloud. So it's a pretty good model for lots of hardware vendors. But ML providers can basically run their software stack and get stuff on Cerebras hardware, right? Possibly with some help from Cerebras. So it's not like it is a true thing that like most accelerators have a more difficult programming model than just trying to put it on a CPU. But basically, I'd say you'll find there's a difference if they talk about the hardware and you can say, bring me your model and put it on the hardware. And Samba Nova has gone a little further than that in that they talk less about the hardware now. They talk about its efficiency, but they say, give us your model or come to our cloud. And it's probably a pretty reasonable thing, but it changes your business model. You don't have to have other people capable of programming your hardware. Does that answer your question? So I guess I'd say most of the machine learning companies that are building accelerators are some way along that spectrum. There is a difficulty programming kind of all of them. Samba Nova is probably a little further towards the services side than most. Okay, so here's another form of something you could call a CGRA, but you could also call a spatial processor array. So in Versal, we talked a bunch about the features in Versal, but one of the things we haven't talked about is it's not just traditional FPGA logic, it also has what they call an adaptive intelligent or AIE engine. So it's not in all the chips, but in some of the Versal chips, they have basically programmable logic and this new thing. And what is this new thing? Well, it's basically vector processors. So remember, vector processors mean SIMD. So, and SIMD is a very logical choice if you're going to put a bunch of processors in an accelerator, right? You want to amortize, you want to kind of keep your instruction overhead low. So this AI engine is a vector processor, and it has local memory that it can talk to. It can also talk to the local memory of, let's see, 2 other AIEs. So there's some sharing of local memory. This AI engine can communicate to this memory, so can this AIE engine. So they can communicate through a small scratchpad memory. They can also communicate using, let's see if I have this on yeah, I think I have it on the next slide. Okay, so I guess what I'm trying to say on this is it's spatial, because you're going to communicate with explicit data motion over a NOC to move your data between processing elements. So that's like an FPGA or a CGRA. But your processing unit is a processor, okay? So it will change what it does over time, has an instruction stream. So it's kind of a mixed spatial but processor. So let's zoom in a little more. So I have this AI engine. It only executes on its local memory, but it also can talk to the local memory, as I said, of 2 other AIEs, so you can share data that way. You can also communicate using these, let's see which one is which. The red wires are basically a NOC, a 32-bit wide NOC, and it's basically like the NOCs we looked at earlier. It's registered on both ends, so I can basically send data over this NOC, but I can send it long distances. I can just keep routing it and it'll eventually, after quite a few clock cycles, get where I need it to go. And let's see, the vector processors have a bunch of different data types. So plasticine was FP32. These AIE engines they can do FP32, and they'll do 8-element vectors, or they can do 8-bit, and they'll do 64-element vectors. So it's a standard trick of like, as the data type goes down, you get more SIMD with the same data path. So they're a little more flexible in operand types, which is probably a good match to an FPGA. And then they have this last style of interconnect, this green thing. And the green one is like unidirectional. It's only going one way here, and in the row above, it's going the other way. That cascade interface is basically like an accumulation chain. It looks like they were looking at some of the signal processing that's done in DSP blocks, and you're often adding up a bunch of numbers in a convolution or a field filter. So this cascade interface is basically implementing that same style of I'm going to add up a bunch of numbers as they flow between processors that you would have in DSP blocks. So that's the way I think of the cascade, is a more special purpose accumulation network that's like inspired by DSP blocks. Does that make sense? Yeah.
You said the red one,
Oh, actually, I got it wrong. The black ones, the black ones are the regular NOC, and these are the routers. That makes more sense. The red is just memory. I don't know. This is their picture. I stole that. I don't know why they put the red things for memory. But, okay, thank you for fixing that. So yeah, that makes more and more sense. The black is the 32-bit regular NOC, and you can actually see the routers. Does that make sense? Okay, how do you program this? So Versal they actually have an open source programming model based on MLIR, but their main one used by their customers, the production model, is you write one piece of software that's like your kernel software. So it's a C++ program that's relatively small with some special templates they've written to let you get at the AIE features and data types, like those vector data types. And so you write one piece of software that's your kernel software, and that goes on one core, or maybe you write a few kernels and they go on different cores. And you write another piece of C++ code that basically encodes a graph. It basically says how do these cores communicate, and that communication pattern is like static. So it's like it gets configured into the NOCs, and they just communicate the same way every single cycle. Okay, so they, in a sense, use the NOC in a static way. Almost use it like bus-based routing. So that's interesting. They have to have a unique, I guess it's the thing that happens with all of these siege arrays right now, is they each get kind of a unique way of programming them. People are still figuring out what's the best way to represent things. So if I compare it to plasticine, it's similar in that it's primarily word-wide functional units operating on vectors. It's mostly bus-based registered interconnect. How it's different from plasticine is they use a processor instead of using like a configured bunch of FUs. So the processor means they can do a different thing every cycle, right? The configured FUs, they do the same thing for a long time. And exactly how they program it is different. Each of them has a unique programming model. Yeah?
I'm under the impression that AIE used the iron framework in Python.
That's part of their open source one. So their production one that most of their customers appear to use is this. And then the iron framework in Python is part of their open source MLIR framework. But it doesn't appear that's what most of their customers use. It seems most of their customers use this flow. But this is closed source. So for academics, you can't use it. Well, you can use it if you just want to program it. If you want to change the compiler, you can. Yeah.
So AIE is on Versal, which is an FPGA, right?
Yeah.
So how?
They've also included an exchange in the Ryzen chips as well.
Yeah, it's also in some AMD processors. So it was brought out in Versal, and the biggest arrays are in Versal, but they're also something called the neural processing unit in certain Ryzen processors from AMD. It's the same architecture, but those ones are more like, I think, arrays of like 32 rather than arrays of like 400.
Because I was wondering how you get C code. I mean, like you would use the hard processor on the FPGA to send C code to the Versal.
Oh, you compile it offline. I mean, it's kind of like you don't send Verilog to an FPGA, right? You compile it and you get a bit stream. They take the C++ code, they compile it down to assembly, well, machine code. They take this communication graph, they compile that to essentially configure all the routers. And the routers, the way they use them is not actually packet switched, at least in their dominant flow. They actually configure them and they effectively use them like registered bus-based routing. Like from this, what I mean by that is it would be, you might have from this AI engine, I am going to go here, right? And there are multiple links, so you could also have another path from this one. I'm also going to have something going here. But in their dominant programming flow that's kind of most productized, these are essentially configured and like all the traffic does that. And that's a slight simplification. So while they can do packet routing, their main programming model is configuring it in sort of a more static way. Does that make sense? Okay, so that's it for that. I have like 7 minutes left. I'm going to keep going. I'm going to go fast. Any other questions on? Yeah, okay.
Kind of reminds me of like a streaming multiprocessor than the GPU.
Streaming.
Lots of small processors talking with memory in between.
I'd say it's somewhat different than that. I mean, it is a processor, so it's similar that way. But I mean, a GPU, all communication is through various levels of memory hierarchy, right? Whereas here, you actually execute only on your local memory, and your communication is explicit. Put it in someone else's local memory, send it over the NOC to someone else. So it's spatial. And in a GPU, that spatial, while there is some spatial locality in a GPU, there's not as much. It's kind of, because it's more of a hierarchy, and it's effectively only exposed as a hierarchy, right? There's like local memory, there's shared memory, and there's like global DRAM memory. So yeah, that's one of the things that can make these spatial processors more efficient is that you move the data where you want, but it also makes them harder to program, right? People haven't figured out how to make that easy to program. Okay, this is the last topic. Actually, I have one more that I'll post after, but I won't even try to get to that one. Okay, it's the wafer scale engine. So one of your readings was this one, the micro paper. The micro paper is from the wafer scale engine 2 generation, 7 nanometers. I've also mixed in some data from the next generation, which is like their current main production line, which is 5 nanometers wafer scale engine 3. So I kind of mixed both those. But this micro paper, I think, is a little bit more of a gentle overview, right? So that's why that's the one I assigned. Actually, what did you, I have not talked about Cerebras stuff in this class before. How did you guys find that paper? Was it interesting? It was good? I actually found the last part, even though I know that's that machine learning programming on the wafer scale engine quite well, I found the last part of the paper was still reasonably hard to understand. So I would say focus mostly on the hardware because the weight streaming model is pretty tricky to get your head around. I don't know if people found that or not. So.
I saw your fiance post and stopped as soon as the question.
Yeah, I intentionally didn't ask any questions about how is weight streaming mapped onto it because I was like, boy, this is actually pretty detailed. I don't know that people are going to figure that one out. So, okay, so there's at least one vote for it was good. Okay, so why wafer scale? So the purpose of use, so I'll show, I guess everybody, hopefully you know what wafer scale is. We're not going to chop up a chip into many little pieces. We're just going to try to make a giant chip the size of a wafer. So why would we do that? So we're trying to make a really big parallel system without the bottlenecks and energy costs of multi-chip interconnect. So this is data from Mark Horowitz from a famous paper he had in ISCA 2014, but the image is from Bill Dolly's Hot Chips 2023. So if you get data from even a pretty energy efficient, this is low power DDR DRAM, the energy to get like an 8-byte word from it, 640 picojoules, okay? That's a lot more than if you got it from a relatively large on-chip SRAM, okay? So if this on-chip SRAM is megabytes, then it's about 50 picojoules per word. And if you make the SRAM smaller, like kilobytes, it's down to 5 picojoules per word. Okay, so what's the lesson of this? As your memory gets more distant, it's more energy to move it. It's also more energy to access a bigger memory, just because of the way they're built. The word lines, the bit lines, they're bigger. So if we can do our processing off of relatively local SRAM, we can save a lot of power. Another part of this presentation from Mark Horowitz is that also this data movement cost is bigger than the compute cost, especially if you're using little operands. Like if you're using small operations like 8-bit, this dwarfs all of your costs of actually doing the computation. So this is like not the second order thing to optimize, it's like the first order thing to optimize. Okay, so that's like the inspiration of why would you do wafer scale integration. It's basically, I would like to keep my compute and my memory nearby and minimize my interconnect cost. So this is a wafer scale engine, the 3rd generation. It's 4 trillion transistors. And its die size is over 46,000 square millimeters. So it's pretty. These are actually screw holes. Like you have to mechanically think about how you attach this. But this is 1 unit, okay? So the NOC goes through all of this without interruption and without bandwidth bottlenecks, actually. This is actually an H100. So Blackwell is actually twice this size because Blackwell, which came out after this picture, takes 2 reticle-sized dice and puts them on an interposer. So NVIDIA is also trying this. Like it's interesting how you see like they've gone reticle limit, then interposers to put 2 things together, but that's still a lot less silicon. So that's, for Blackwell, you can think of having 2 of these things on an interposer, right? An interposer is still not as good as wafer scale, but it's better than a circuit board. So that's the scale. Okay, what does the architecture look like? So the paper you were reading was wafer scale 2. This is 3. It's not that different, but it's a little different. So I'll just focus on it. So it's a small core. So on this wafer scale engine 3, it's 900,000 processors. Okay, so there's 900,000 processors on this. Each of them has to be pretty small. So it's got 48 kilobytes of SRAM. It's got a very small, explicitly managed cache. That's just so you can keep all your function units busy. And this is not for instructions. This is for data. And then you've got basically SIMD units. So if you're doing 16-bit operations like FP16, you can do it 8-way. If you're doing 8-bit wide, you can do 16-way. To keep the core size small, it's in order. So no complicated out-of-order energy hogging instructions. It's like scalar, so you're 1 instruction at a time. As I just said, it's SIMD, right? So we're trying to amortize the cost of the instruction fetch and decode. The instructions are quite CISC. So everybody knows RISC versus CISC, I assume, if taking computer architecture. Okay, so the operands, okay, so in RISC, you have a simple operation that does things like everything's in a register. You add these 2 registers together, right? That's a RISC operation. Okay, so the instructions in the wafer scale engine can be up to 4-dimensional tensors for various operands. So it could be, I want to do a multiply accumulate between this tensor and this tensor. And I'm going to describe this tensor with a 4-dimensional access pattern, right? Like from 1 to 50 in the first dimension by strides of 2. And from 3 to 300 in the second dimension with strides of 4. That would be a valid way to describe it. Often it's like you could describe it with just 1 dimension, right? Like I just want to go through a vector of length 100. But you do actually have the capability and often do use these more complicated things. Those don't execute in one cycle, right? That basically, what it does is the instruction is encoding, get me the data out of SRAM, it's got to be in SRAM, and feed it to the SIMD units, and then update your internal counters so you're ready to get the next data. Okay, so if I'm going to walk through like a vector of like 300 things or a matrix of 10,000, it will take quite a few cycles. But the instructions are coding everything, right? Like where do I go to get the next data? When do I stop looping, et cetera. So it's similar to a DSP processor in that way. So if you remember back to the Texas Instruments DSP processor, I told you they use CISC instructions so they could do things like zero overhead looping. Like a single instruction could actually encode, I want to add these 2 vectors together. So it's similar. It means that issuing 1 instruction per cycle, you can keep these execution units busy. Because every cycle I could have, for example, 16 8-bit numbers ready, and other logic is basically updating all my internal counters and stuff and getting ready to get the next data. Does that make sense? But in an energy efficient way. I didn't have to actually go and fetch like 4 instructions and do multi-issue and stuff to try to line all that up. Another technique to optimize for throughput computing is each core has a main thread and 8 microthreads. So the microthreads are described in the micro paper. Basically, if data is not ready for some reason, and one of the reasons data is not ready is this, I said this is always executing from SRAM. It's not quite true. It's SRAM and data arriving from the routers, the fabric. So maybe the data is not there yet, hasn't arrived. The core can basically in one cycle. Like every cycle, it decides, can I make progress on the main thread, or should I just switch to one micro thread? And the micro thread can tell me to do something else. Maybe get some data from the fabric, maybe send some data out to the fabric, maybe do some housekeeping. And the idea is with low cost to keep the processor doing something every single cycle. Does that make sense? So it's kind of using multi-threading as well. This is the picture from the wafer scale engine 2, but it's similar in the next generation. Half the area is SRAM, okay? So this chip is about efficient execution units and lots of SRAM, okay? And one more thing, efficient communication. So up here is this fabric, okay? So the fabric is how do I connect to the routers and how do they connect to each other? So the fabric is 32 bits wide. It's a mesh. So meshes are there's lots of good anecdotal evidence for meshes. And it's basically the nearest neighbor of communication in the mesh. So you go one hop to the next router. You're registered at every router. So it will take you quite a few clock cycles to get all the way across the wafer, but you can do it. Let's see. So much like the AIE engines, you have explicit data movement, right? There's no caches. There's no global address. If you want data, you can get it from your local SRAM. If you need other data, it has to be sent to you. The interconnect's a bit more flexible than the AIE. So you've got 32-bit links, but the fabric router itself basically has 24 virtual channels. The Cerebrus calls these colors. Every color is basically a different entry in the routing table. And whenever data arrives, it arrives with like a color ID. So the color ID is enough to look up in the routing table, where do I go? So you can think of that as essentially like you're multiplexing a bunch of different routes over the same wires. So you can think of the colors like virtual channels, or you can think of it as they're allowing you to multiplex your routes over the same wires. Whereas at least the dominant programming model that AMD's made for the AIEs, you're kind of just always using the same route over the same wires. Okay, so it's a bit like registered and multiplexed bus-based FPGA interconnect. So it's spatial, but it has all those differences. The compute model is streaming data flow. So data arrives from the routers, from this fabric, and it triggers computations. So that comes in, and it can trigger the processor to, okay, what do I do with this data? Maybe it was a control word that tells me, go jump here and start doing this. Maybe it's data I've been waiting for, so I continue with my matrix multiply. But basically, yeah, computation is triggered by the data arriving. When you compute some outputs, you can put them back in your local SRAM, or you can send them back out onto the fabric to go to some other processing element to keep doing work on it, or you can broadcast it to a whole bunch of them, et cetera. So yeah, it is streaming data flow. The whole NOC has latency, has buffers, has back pressure, so it's a latency insensitive design style. I guess I talked about some of this. So there's a lot of similarities to the AMD AI engines. So spatial processor arrays that you can consider a form of CGRA. They're vector processors. Your data movement is explicit. Your programmer says where the data goes, and use a mesh NOC. Some differences, the AMD AIEs have this cascade interconnect that looks like it's designed for efficient accumulation for signal processing. So it might also reflect the heritage of thinking about AIE engines as how do we use them as really good DSP blocks. I just talked about this. The routers are a little more flexible in the wafer scale engine, where they have these colors that allow you to kind of multiplex different routes on top of each other. And the cores themselves can task switch because they have these multiple, they're the main thread and they have these micro threads. They can switch between tasks. And the instruction, these data structure registers in Cerebrus are pretty different, right? So the instruction set is kind of unique, more DSP-like, very CISC. Okay, so let's talk about wafer scale. So this image is from the micro paper. So it's wafer scale engine 2. So you got this core, it's quite small. You replicate that a lot to get 10,000 cores in a reticle. and they replicate that reticle 84 times across the wafer to get the whole thing. So within a reticle, here, your fabric is basically just, it's a NOC with registers at the input and output of the routers. 32-bit wide buses with the valid bit and a back pressure bit and so on. So conventional, takes like a clock cycle or two. When you cross a reticle, you have fewer wires because some of the things we talked about with interposers. But it's enough that Cerebrus can build a source synchronous interface. So that's the same technology, the same style that you use with DDR. So a clock with a certain set of data bits in order to get enough bandwidth from the wires crossing a reticle that they can match the bandwidth of the NOC. So the reticle boundaries are almost transparent, right? They are transparent to software and they don't have any impact on bandwidth. They do have a modest number of cycles that they add, so they're not completely transparent from a latency perspective, but not enough to affect the software or the bandwidth. The odds of yielding this thing are like 0, right? If you did not have some redundancy. So every slide I'm showing, I made sure I took from public sources. This is actually a screen capture from a YouTube video by the CTO. Because until I found that, I was like, I did not know I could actually show a picture, but it's like, this came from Sean's YouTube, so it's out there. So Cerebrus does use redundancy, right? Otherwise, you'd never be able to yield this. So this is the software and programmer view of the chip. You have these processing elements with routers, and they're in a mesh. But there are actual redundant links. If this processing element is broken, there's a redundant link that lets you go around it and then come back down. Okay, so another redundant link. So that means that the testing of the wafer can identify broken PEs and broken routers, and you can then basically store that information. Some low-level software can configure the wafer with the appropriate redundant links. And basically the rest of the software stack doesn't need to know about it. And that's a similar idea to what Altera does. It's not the exact same mechanism, but I think for any redundancy scheme, it's very important that most of your software doesn't know about it. And that's the case here. The end users, almost all the software developers, they do not need to know anything about this. It's kind of invisible to them. Key use case so the wafer scale engine wasn't built just for machine learning. It's actually quite good for things like partial differential equations. Remember the lattice methods that I talked about in programming models, where you assign certain points in a physics problem to certain processing elements? That actually works very well with this as well, because you have so many processing elements. But machine learning is obviously the biggest opportunity around. So the number one use is machine learning. In the micropaper, it talks about training. What I'm talking about here is inference, so the opposite. So you've got a model, you want to answer questions quickly. So if I have an LLM, what Cerebrus does is they basically take different layers of the LLM, right? So you might have 80 layers in an LLM, a large language model, allocate them to different parts of the wafer. Okay, so you got a whole bunch of PEs here. They're going to collaborate to together multiply a matrix, then together do attention calculations, etc. So this is a very distributed compute. But they produce their output, they feed it to the next layer, right? The output is basically a vector. And then it goes to the next layer, and the next layer, and the next layer. And eventually you get an output token. So it's like you can map that into a word, you send that to the end user, it goes back to the input, and now you can compute your next token. So it's autoregressive, and we talked about that earlier. Autoregressive means it's latency sensitive, right? We've got a loop here. To make this low latency, all the weights are stored on wafer. Okay, so it's all that SRAM. The weights are distributed across all the PEs so that you don't have to go out to DRAM. And that allows you to do massively parallel compute with the data very close to you, which gets you very low latency, both high throughput and low latency. And this loop is, from a Cerebrus perspective, beautiful, right? Because it means that there's this latency bottleneck that you can't solve by just, for example, taking more and more GPUs and putting them in parallel. That won't improve your latency. Does that make sense? So does anybody see any trade-off to this? Like this all weight stored on memory. Okay, I showed you like the Mark Horowitz and Bill Dowley slide that says that's great for energy. It's obviously really good for bandwidth and computing. Any downside? Yeah.
All you guys are so sweet.
Go for it.
I was gonna say that means you're limited by the total memory on the wafer.
Yeah, so your downside is it's kind of like the FPGA, right? Like once you're out of on-chip memory, what do you do now? So there are a few things. I mean, you could say, well, I'll use off-chip DRAM. And Cerebras can do that, but obviously it washes out the gains. So what they generally do actually is put multiple wafers in series. So this is not an unreasonable thing to do. Like you don't know the size of these systems. So you basically put certain layers on certain ones and you build them in a pipeline. And the network links in between these are pretty low latency. Like there's so much processing going on, it doesn't slow you down very much to have have network links in between these things. It does mean that as the models get bigger, you do need more wafers. Although because it's a pipeline, you have more users in them too. So you get more throughput because your pipeline's been unrolled in space, but you did have like a minimum size in order to use this compute model. So for example, for Llama 70 billion, this is showing like 140 gigabytes of memory if you do FP16, which means that you need 4 wafers. If you push that down to FP8, then you could do 2 wafers. So you can see this also demonstrates what are some of the gains of why do people push so hard to try to get the precision down. It's partly to make the compute units smaller, but it's also to get the memory footprint down. How well does this work? So I actually just took this off Cerebras' webpage. So you might say it's propaganda, but it's propaganda from this is artificial analysis. So it's a group that goes off and does analysis of like how fast are all these LLM inference services. And actually this data was published by this company, right? Because this is the highest number that's ever been achieved for Blackwell. Okay, it's much higher actually, quite a lot higher than, for example, what Azure or Amazon are getting, okay? This is not one Blackwell. This is a whole bunch of Blackwell chips ganged together. So you can't actually host these models on like one GPU either. So they took a whole bunch of Blackwells together, but they got better performance using some very clever partitioning techniques and so on. So that's why like their performance is better than anybody else's. But the Cerebras numbers are still like a lot better, right? So nearly 10 times better. So you do get a lot of throughput from this near memory computing style. And you can see Samba Nova, right, which is one of the CGR we talked about, is also on here, also one of the top providers. So, and then the last one, which we haven't talked about because it really can't be considered an FPGA-like thing, but Grok, so another company here in Toronto. So anyway, so lots of interesting things happening. There's like lots of competition for who has the fastest inference. Yeah. So I think that's the end of my slides. Sorry for going over time. So yeah.
I'm a visual learner. What does this shit look like?
Oh, okay. So I actually brought one of these in. Okay. So this is like 4 trillion transistors. I don't want to break it because the list prices are not. I can't even figure out the list price except by doing web searches. But the web. Basically, speculation is somewhere in the $600,000 to $1 million range, so don't drop it. So you come up and take a look if you'd like. Yeah, it's fine.
So is this a functional chip, or is this?
It probably doesn't work.